Good morning. It is my pleasure to welcome you today to the School of Civil Engineering at the Universitat Politécnica de Valencia. You have a very interesting workshop ahead, preventing structural failure propagation. Civil security for society is one of the main topics highlighted in the Horizon Europe 2021-2027 program. I would like to congratulate Professor José Miguel Adam and all his team at the Building Resilient Group for the organization of this up-to-date event. It is going to be a success for sure. Our school is also updating its academic offer. Besides our classical civil engineering bachelor and master program, for the next academic year, we will have a bachelor in transportation and logistics management. We are also planning to offer a new bachelor degree as well as a Master Erasmus Mundus on sustainability in the very near future. The topic of this workshop, as well as the changes we are pursuing as a school, are just examples of how we, engineers, have to adjust to our environment, taking advantage of our problem-solving capacity to lead and to stay ahead of the issues that need to be dealt with in our society. Welcome everyone to our school and enjoy the workshop. Thank you very much.
Okay, good morning, everyone. I'd like to welcome you all to this workshop, which we are organizing at the UPV Civil Engineering School. And well, this workshop is part of the communication and dissemination activities of the ENDURE project, which is funded by the European Research Council, the ERC. And well, I prepared a few slides for this short introduction. First, I'd like to show you who we are, the research group. And second, I'd like to provide some details about the UPV Civil Engineering School. As the director mentioned before, we are now at the Civil Engineering School. And since this workshop is organized within the framework of a project funded by the ERC, the European Research Council, I will briefly describe the main aims of the project. And finally, I share with you the program of the workshop. Let me give you some details about the research group. Well, I mean Building Resilient, where we research. So we are a research group at the UPV working in the field of structural engineering, and our research aims to improve the resilience of buildings and bridges, and we mainly work in two areas, structural assessment and structural robustness. Our work in these fields is usually associated with large-scale experimental campaigns combined with computational modeling. Our work in these fields, well, we do our research at the ICTech Institute, which has one of the largest structural test laboratories in Europe. And the research we do right now is funded by different public entities, such as the European Commission, the European Research Council, or the Spanish Ministry of Science and Innovation. So, as I mentioned before, we are now at the Civil Engineering School facilities. And, well, the teaching activity at the Civil Engineering School covers different aspects, such as environment, hydraulics, roads, city planning, structural engineering, geotechnics, or ports and marine infrastructures. The Civil Engineering School has 2 degrees and 5 masters right now, and some of them will be implemented during the next years. And 2 degrees, one in civil engineering and the other in public work and engineering. And one of the degrees is combined with mathematics as a double degree. We also have 5 masters, civil engineering, planning and management in civil engineering, transport, territory and city planning, environmental engineering, and transport intelligence systems. The school has agreements with different European entities for double degrees or masters, and in addition there is a double degree with the Illinois Institute of Technology from the United States. Regarding the project funded by the European Research Council, which funds this workshop, this table shows the main details. The project was funded by the 2020 Consolidator Grant call, and the acronym is ENDURE, and the title, Fuse-Based Cementation Design Approach, Avoiding Failure Propagation in Building Structures. The budget is 2.5 million euros, and 8 people will work full-time for the project, apart from other researchers working part-time. Regarding the science behind this project, we know that the aim of current building design philosophies for avoiding progressive collapse is that when a critical element fails, for example a column, alternative load paths should exist to redistribute the load of this element to the rest of the structure. This is normally achieved by providing a building with extensive continuity through suitable tie-in systems. Designs based on current approaches have been effective in many extreme situations. For example, the terrorist attack on the Cobalt Towers, shown in this picture. And actually, this building suffered major damage without collapsing. Sorry. However, in certain scenarios, our design philosophies are ineffective or even increase the risk of progressive collapse. Here, I have compiled some of these scenarios. And in these situations, when slabs and beams are firmly tied together, the risk of progressive collapse may actually be increased. The continuity means that when a part of a building collapses, this part pulls the other zones, leading to further collapse. So in view of this, new research is necessary to get over the limitations of the current design philosophies. The overall aim of ENDURE, the project, is to develop a novel fuse-based cementation design approach to arrest the propagation of failures in building structures. This new approach is similar to how electrical networks are protected against overloads by connecting different segments with electrical fuses. We want to protect buildings against progressive collapse by connecting building segments with structural fuses. These fuses will provide continuity for normal loads or small initial failures, yet will separate the different segments in situations in which failure propagation is inevitable. As shown in this slide, ENDURE is based on 3 research work packages and another one for dissemination and communication. In work package 1, we are developing a performance-based approach for the design of fuse segmented buildings. In work package 2, we will design, manufacture, and test fuses. And in work package 3, we will implement and validate the new approach in 2 full-scale buildings, one made of steel and the other made of concrete. After this overview of the ENDURE project, I want to share with you the program of the workshop. So we'll have 9 presentations. The first one by Professor Uwe Starossek. Then Manuel Buitrago will continue. Antoni Cladera, Luca Pelà. Well, we'll have a break at 11. And then we'll continue with Luca Pelà, Jason Ingham, Rigoberto Burgueño, and David Stevens. And after the lunch break, we have 2 additional presentations by Bing Li and Itsaso Arrayago. So I think that we can finish with this introduction, and Professor Starossek, the floor is yours. Thank you very much.
Good morning.
Uwe, I can introduce you, okay? That's important. Let me check the microphone. So Uwe Starossek has obtained his civil engineering and structural engineering degrees from Aachen University and Stuttgart University, and he has worked for 20 years as a practitioner in Germany and abroad. For another 20 years, he has been a professor of structural engineering at Hamburg University of Technology. Uwe, thank you very much for coming to Valencia.
Thank you, Jose. First of all, I would like to congratulate Professor Adam and his colleagues on this achievement of having obtained a major European grant, and I gladly participate in this endeavor as an advisor. I would like to give this review from a somewhat more personal perspective, considering this particular occasion and the kind of audience we have here. That is how I came across the topic and what I have learned about it. My involvement with progressive collapse began in the 1990s with the design of this bridge between Prince Edward Island and the Canadian mainland. I had just joined Jean Moulin's design office in San Diego when we were appointed the main design consultant for this project, which was special in many regards. It was privately financed, a so-called build, operate, transfer project, and the bridge was to be designed and built in just 4 years, which was made even harder by the harsh environment as the Northumberland Strait, which was to be crossed by the bridge, is covered by ice for 5 months per year. All this led to a special design and construction concept. The entire bridge was assembled from very large concrete elements that were precast on shore and post-tensioned on shore and on site. For limiting the number of piers and the obstruction of the strait, a quite large regular span of 250 meters was chosen. The largest precast elements were the so-called cantilevers, which extended from a respective pier to both sides and had a length of 190 meters and a mass of 9,000 tons. With such an extraordinary project, many new problems arise and must be solved. A question that was posed to us by the building authority was, what if one span fails for any reason whatsoever? Will such failure remain limited, or will it trigger an overall collapse of the bridge? As the main consultant, one of our tasks was to set up the design criteria for the entire project. So it was upon us to also define the special criteria for preventing progressive collapse. The expectation apparently was to prevent a collapse progression after a failure of a bridge pier or a bridge span. We soon realized that in such a scenario, it would be impossible to design alternative load paths that would bring such an incipient collapse to a halt. The only possibility we saw was to isolate such incipient collapse by some kind of segmentation. At this point, it was necessary, and we could it was necessary and also possible to establish the design objectives more precisely. In particular, it was decided that a collapse should not extend over more than 2.5 spans. A stricter requirement was deemed to be impossible to be met, and it was accepted like this by the client and the building authority. Having established the design objectives, we could start with the analytic verification of the structure and its redesign. I would like to present you the most important step of this verification and redesign. One of the scenarios we studied was the sudden loss of the vertical support of a drop-in span from its support on a cantilever tip. On the other side of the drop-in span, it was connected monolithically by a cast-in-place joint to another cantilever. We found by analysis that in such a scenario, a bending failure would occur at the cast-in-place joint, and the drop-in span would start to rotate about this point, that the continuity tendons would come to bear on the bottom slab of the cantilever, and we thought that the bending the tendons, these continuity tendons, would cut through the bottom slab and eliminate the bending moment capacity of the cantilever. We further expected that this collapse would progress towards the pier and possibly beyond into the next span. At this point, our analysis became more and more speculative. It couldn't further be based on an exact analysis. In any case, we were not able to show that the collapse would not progress into the next span, so we could not prove that the design objective was met. The only possibility we saw to remedy the structural response and also the predictability of the structural response was to change the design concept and the articulation of the bridge. We see here the preliminary design, the articulation, the design concept of the preliminary design. In every second span, the drop-in span was to be connected by a hinge on one side and monolithically by a cast-in-place joint on the other. In the remaining spans, the drop-in span was connected monolithically at both ends to the respective cantilevers. And because of the study I had just mentioned, this was changed in the final design. Instead of a monolithic connection, the drop-in span was connected to the other cantilever by a second hinge. This means that the continuity tendons at this location are eliminated and the structural response becomes predictable. In particular, the drop-in span will rotate about this hinge and at a certain rotation angle predictably disengage from the tip of the cantilever. Now we could safely design or verify the remaining structure for the forces that occur during this process, the rotation of the drop-in span and its final sudden disengagement, its final separation from the cantilever. First, we computed the support forces on the hinge, which is located at the tip of the cantilever. The support forces which occur during this rotation, the falling of the drop-in span. We considered two different support conditions, a fixed support and a horizontally sliding support, and established the equations of motion for each case. Both are nonlinear second-order equations, differential equations, which we had to solve numerically. Interestingly, it is possible to find closed-form expressions for the support forces, not as function of time, but as function of the rotation angle theta, which in turn is related numerically to time after solving the differential equations. I should mention perhaps that all this work, from being confronted with the progressive collapse concern until having redesigned the bridge, or revised the preliminary design of the bridge, had to be done in less than 2 months. So this work was done in a very short period of time. And we had to develop our own methods as good as we could. Well, now we have calculated the support forces. Here we see the vertical support force as a function of time. When the support on the other end of the cantilever is lost, the support force suddenly drops to half its value. So instead of 1,000 tons, it's only 500 tons. The total weight, or the total mass of the drop in span, is 2,000 tons, its length is 60 meters. Here starts the rotation. The vertical support force increases again until it suddenly drops to zero at the moment of final separation. We see here a highly dynamic excitation force acting on the remaining structure. When this dynamic force is applied on a single degree of freedom oscillator, this displacement as a function of time results. We see it here. We see here the vertical displacement of the cantilever tip related to or normalized to the static displacement. The static displacement when the drop in span is taken off slowly. In this kind of presentation, we can see that the dynamic response can be larger than twice the static response. Now, all the remaining structures, there were many of them, were different and all had different natural periods of vibrations. Because, it's important because this response, of course, depends on the period of vibration of the system we consider. This was for a single degree of freedom system with a period of 1 second. Now, we had many different systems to consider, and therefore we developed a response spectrum for this kind of force excitation. And that is shown here. This is the response spectrum, again normalized to the static displacement. And it means the maximum dynamic displacement as function of the natural period of the system. Now we knew that the remaining systems had all different periods, but all were around 2 seconds. And from this we could select, here we have 2 seconds, a value of 2.6 as a dynamic amplification factor to be used for the entire bridge, to be generally used for the entire structure. The remaining structure or structures, it's a little slow. Here we go. So the remaining vertical, the force amplified by that dynamic amplification factor, the static force multiplied by this amplification factor was used in a quasi-static elastoplastic verification of the remaining structure. When that force is applied at the cantilever tip, a first plastic hinge forms at the top of the first adjacent pier. The bending moments are redistributed in the system accordingly, and the second plastic hinge forms in the first adjacent span. Mild steel reinforcement is added around that location to ensure equilibrium. The most important lessons, perhaps, learned in this process was the designer practice were established based on judgment together with the client. Actually they were developed by us and agreed to by the client. This concern of the authority was posed to us not as a well-defined requirement, but more like a concern we should think about and do something to prevent such an outcome of progressive collapse. So this already was very particular to me and very different from any other work I had done. We learned that robustness can be increased by segmentation, not only by continuity, as you often will hear, but also by segmentation, which can require a reduction of continuity by inserting hinges. And this also improved the predictability of the structural response. So this concern of predictability also can be a reason for design decisions. The segment borders were formed by isolating elements that are able to sustain large displacements, the hinges we have inserted, or large forces, strong elements. In this case, the adjacent pier and next span, we verified that they would resist the forces during the fall of the drop-in span. And the verification of the remaining structure, in this case, in this design work, we used the plastic capacity of the structure in this verification. A few years later, I became a professor at Hamburg University of Technology, and I had the time to reflect on this previous project-related work. And I asked myself, why did we have to invent all this approach ourselves? Why couldn't we base this work on established methods and standards? To answer this question, let's have a look at the basis of our ordinary design. It is based nowadays on reliability theory, which is a stochastic mathematical theory. In theory, it provides a uniform level of safety and economy for the structure. This is not the case, however, for structures that differ in their sensitivity to initial failure, because this sensitivity is not factored in the analysis for practical reasons. It is very difficult to consider this sensitivity of the structure to an initial failure. Other problems are that the input data that are needed for this analysis, that is the probabilities of actions and resistances, and the admissible probability of failure are not available, at least not when progressive collapse is concerned. How or what is the probability of an event that has never occurred before? Or how should we ever agree on the admissibility of the probability of a catastrophe? Well, I think that a different approach is needed for progressive collapse. For the time being at least, we are not able to use stochastic methods. We should base it on deterministic thinking. And to start with this alternative approach, which I want to suggest, let's look at various definitions of robustness which have appeared in the literature. According to the Joint Committee on Structural Safety, robustness is defined as the ratio between the direct risks and the total risks for a specified time frame and considering all relevant exposure events and so forth. It's quite a complicated definition. It's very long. I believe a good definition should be concise and short. Most of these definitions are very long. This one, the Joint Committee Structural Safety definition, it might be correct in the context of reliability theory, but it doesn't seem practical. How would you specify, define, or quantify this ratio. A ratio is a ratio of numbers. So what number do you give to the direct risk and the total risk? I don't believe this to be practical. The other definitions are more intuitive and more practical, but they're all more or less long. They also differ from each other quite considerably. What most have in common, although is the notion of insensibility to initial failure and the notion of disproportionality. Now this mostly appears here. So I would like to suggest a more concise, other problem here is this insensitivity and disproportionality is not explained. How would, it is left open, not explained, how this data is obtained, or how would you define sensitivity and disproportionality. So this leads to the following suggestion. The insensitivity of a structure to initial damage, that is robustness. Or more explicitly, a structure is robust if an initial damage does not lead to disproportionate collapse. For a precise definition, we need to define initial damage and disproportionality. And this is done by referring to specified design objectives. A structure is robust if an initial damage, as determined from the hazard scenarios, does not lead to an extent of damage that violates the performance objectives. And hazard scenarios and performance objectives are the design objectives to be specified beforehand. The hazard scenarios are the abnormal conditions assumed to occur for the design against disproportional collapse. They can be specified as specific abnormal events, as notional actions, or as notional initial damage. The performance objectives are the acceptable sum of all direct and indirect losses. They can be specified as acceptable extent of collapse and acceptable other damage. We have tied the definition of robustness to hazard scenarios and performance objectives. It remains to be clarified how these design objectives are established. So this is perhaps the most important point. The design objectives are specified by the client and a decision-making process based on engineering advised and approved by the authorities. The client is defined as the collective of the owner of the structure and other stakeholders affected by its possible collapse. Other stakeholders are external parties affected by the decisions concerning the project without having a direct involvement in it. For example, other authorities, utility companies, insurance companies, occupants, neighbors, and others. Defining the collective will of the client can require an administrative or political decision on a local, national, or international level. This concept of client and client-based design objectives is admittedly unusual, but it is deemed, I think it is justified and practical, at least for very large projects like the Confederation Bridge. For more normal-sized projects, it might be possible to select the design objectives based on guidelines, which, however, would probably be specific to the type of structure. Here you see a suggested framework for the specification of hazard scenarios. That can be threat-specific abnormal events, notional actions, or notional damage, depending on the requirement level. For instance, a basic requirement, notional damage, would be the sudden failure of one small component, for instance a building column, a bridge stay cable or hanger, and for higher requirement levels accordingly a higher number of such initial failing elements. And also for the performance objectives, the other part of the design objectives, you see a suggested framework for the acceptable extent of collapse and the acceptable other damage for the different requirement levels. For instance, the basic requirements, acceptable extent of collapse, would be 10% of the structure in terms of masses, volumes, floor area, or costs. The respective number for the Confederation Bridge was 5%. Yeah, when you compare the 2.5 spans that were allowed to fail in comparison to the 43 main spans and further adjacent spans, that amounts to roughly 5% of the structure. And, well, it is possible to develop a whole framework of definitions, concepts, procedures, and model guidelines in this way, in which also the design methods have their place. You see a classification of all possible, I believe, design methods. There are design methods that aim at increasing robustness and other methods that reduce vulnerability or exposure. For very large structures, it is recommendable to base the progressive collapse design on increasing robustness. And there we have two methods available, the alternative load path method and the segmentation method. Alternative load paths, which are usually recommended for buildings, and segmentation as it has been used in the Confederation Bridge and also in some other bridges. When we have the choice between these two methods, perhaps this comparison might be of interest. In particular, we find that the alternative load path method is sensitive to the size of the initial damage, which means it becomes ineffective for large initial damage, whereas the segmentation method is insensitive to the size of the initial damage. On the other hand, in segmentation, the extent of collapse can be as large as one segment, which means it can be relatively large, whereas in the alternative load path method, it would be usually small. So the alternative load path method is preferable for small initial damage and segmentation for large initial damage. Now remember that the size of the initial damage and the acceptable extent of collapse are two of the design criteria to be established for the project. And this means that the choice of the design method not only depends on the structure, but also on the chosen or given design objectives. And this brings me to the conclusions. Design based on reliability theory does not provide a uniform level of safety and economy and cannot prevent disproportionate collapse. A consistent framework of terminology and procedures for design against disproportionate collapse is offered. Disproportionate collapse can be prevented by a deterministic approach in which the design objectives are established and a decision-making process. Various design methods are available in this approach. Their applicability depends on the type and size of the structure and on the design objectives. Thank you for listening.
So thank you very much, Professor Starossek. We can move to the next presentation. introduce Dr. Manuel Buitrago. Manuel Buitrago is a senior researcher at the UPV, and he has received different postdoctoral grants, and is now beneficiary of Juan de la Cierva Grant, one of the most competitive in the structural engineering field. Currently, his research activity focuses on the robustness assessment of buildings and bridges, being responsible for the planning and execution of full-scale tests carried out in the research group. Manuel, the floor is yours.
Thank you very much, Professor Adam, for the introduction. In my presentation, I will show you the full-scale tests we carried out in our research group, but only that ones that were focused on the robustness assessment of buildings and bridges. Maybe just I divided my presentation into 3 parts. In the first part, I will define what robustness means, and also the research lines we are carrying out at Building Resilient Group. And then I will describe the full-scale test we carried out in the past. It's not working again. Yes. Let's move on the robustness definition. Before this, I think you are really familiar with the progressive collapse definition. Progressive collapse is what happens when a local or initial failure propagates to a large part of a structure. We have here the classic examples. We have here the Roland Point building and the Oklahoma building, where an explosion produced a local failure on the structure, and then it propagated to a large part of the building structure in this case. We have also the case of the Quebec Bridge, which is also another classical one at the beginning of the 20th century, in which a buckling of a single element produces during its construction the propagation of the failure until all the bridge. Within this context, we also, it appears the robustness concept. The robustness concept is, as Professor Uwe said, has a lot of definitions, but we can understand it as the insensitivity of the structure to a local or initial damage. In that cases, in the top pictures, we can see how these structures, a building, a bridge structure and a building bridge, was insensitive to the local failure of a pile or of a column, respectively. Then, in the bottom picture, we can see the cases of the steel truss bridges, in which we are seeing that failure of a really big important element, which is a bottom cord, does not produce the propagation of the failure through the structure. Regarding the lines of research of our research group, we can say that we have 2 main lines of research, one with steel truss bridges and another one applied to building structures. And inside these 2, we have different studies, one for structural assessment and another one for robustness assessment. In this presentation, I'm only going to be focused on the robustness assessment. Well, speaking about the steel truss bridges, we have some full-scale tests to assess the robustness of the bridges, of this kind of bridge, but also to establish practical recommendations, inspection protocols, and monitoring systems just to control them in a safe way. In the other part, in the building structures line of research, we did in the past some structural assessment to masonry structures, like a cross-bolt and a masonry building, but I'm going to be focused on the robustness part that we carried out several full-scale tests on concrete structures. Concrete structures that were built or well controlled during construction, and with different kind of structure. One with cast-in-place concrete, without and with infill masonry walls, and one, and this is the last test we carried out, one with precast concrete structures. Then, as Professor Adam told you, we have now a project with the fuse-based segmentation approach. Well, all of this is able to do because, we have also available large facilities here at the university. We have available the ICTech laboratories, which is one of the largest laboratories in Europe. And also when the test or the structure is really risky, or the building or the bridge is really long, we have also we can take also the space that we visited today. Some of we visited this place today, yesterday, sorry, in like an outdoor laboratory, a courtesy of the company Link. Let's move on to the description of the full-scale test we carried out on buildings. First of all, I would like to show you one of the branches of our research line, which focused on buildings during construction, and this is motivated by some of the collapses on the. Sorry for this, but it's working quite badly. Can you play the video, please? So what we are, it is motivating because, you know, one of the stages during the life cycle of a building, which is more risky, is the construction stage of a building. So in this video we have seen the collapse of a building in New Orleans during its construction, and after a literature review of several case studies that we did in the past, we found that the most repetitive cause of collapse during construction was the overloading of the shoring system during the construction. So for that reason, we developed, or we tried to solve this issue, developing a new device, which is called load limiter, but it works like a structural fuse here installed on a shore. This device is working well under a behavior which is elastic linear until the formation of 3 plastic hinges on the upper part of the device, and in this way we can control the load that the shore is receiving. We can see here better this behavior in this graph. So a conventional shore behavior without the load limiter is elastic linear until it's brittle failure, okay? But if we install the load limiter, we have this kind of ductility part on the shore behavior. So the load is limited to the admissible load of the shore, and in the mean way, with limiting this and with this plastic behavior, we allow the shore having vertical displacement, very little vertical displacement, and in this way we are redistributing the excessive load that this shore is going to receive to the neighbor shores. So in that way we can take advantage of the strength of the complete shoring system. In the video we can see how we install this load limiter in a shore. After developing this device, what we did is a full-scale test where we... Can you put the play on the video, please? Where we validated the device in a full-scale test of only one floor and one bay. And this floor was supported by 4 steel columns that are here. And then with a shoring system, which was really highly monitored. On the top of the shoring system, we built a slab, flat type slab. And we are seeing the reinforcement of the slab in 2 layers and in 2 directions. And all the shores, I have to say that all the shores had the load limiter installed on them. Okay. So after the reinforcement, we pour the concrete on the slab. And after pouring the concrete on the slab, we did a traditional operation on the shoring system, which is the partial streaking or clearing, which consists of removing the half of the shoring system, keeping the other half connected to the slab, and then we simulated virtually the pouring of the concrete of a second floor by means of a layer of sand and also water on pools. Okay. With that way, we checked that the device was working well. The shores were loaded under its admissible load, and if they were not load limiters in these shores, we had a load on the shores more or higher than the admissible load on the shoring system. So now jumping to another full-scale test. In this case, I'm going to speak about the cast-in-place concrete structure. We did a robustness assessment of this building, just submitted to sudden column removals. In this case, the study was focused on the sudden removal of corner columns. We had in these pictures, in the bottom right picture, 2 steel columns that are prepared for collapse. And we put these steel columns in the corner ones. The building has two floors, 3 meters high each one, and also has a span length of 5 meters. So the overall dimensions of the building is 10 meters per 10 meters. Well, on the top pictures, we can see the building during construction, the foundation, the first floor columns, and also the preparation of the second floor for pouring the concrete. Then in the picture, we can see all the monitoring system we use for this test. Going directly to see the videos of the test, we can see that, well, we have here a column prepared for collapsing with 3 hinges, and only with a little bit heat here, we destabilize the column, and we, in this way, can assess the alternative load paths that the structure is able to activate after the column removal. What we found here in this test was that the vertical displacement was 5 centimeters, and the overall behavior of the structure is like a Birendel beam of the first floor building. Like it's working like a block, like a complete block. Okay. Then in a second test, what we did was to include some masonry panels in the first floor, and we did the test in the opposite corner than in the first test. So with these infill panels, we searched for the activation of another alternative load path. So after unblocking this hinge, the column was suddenly removed, and we found here only a displacement of 0.7 centimeters, from 50 to 0.7. So we found that, of course, the infill masonry panels act during this kind of actions. Well, and another test we have carried out recently, it was in a precast concrete structure. The precast concrete structure had dimensions like the span length is 5 meters in this direction with 3 bays, and 6 meters in the other directions with only 2 bays. So the overall dimensions are 15 meters per 12. The precast construction was made by concrete columns with a unique element from the foundation to the top of 6 meters high. And then we had also semi-precast or partially precast beams on the perimeter and also on the middle line, and precast hollow core slabs that were only pre-stressed with pre-stress reinforcement. Then at the end we poured concrete for the topping of the slabs and also for the top part of the beams. With the topping concrete, we put the reinforcement on the beams, also with the tying force method defined by the DOD, and we had some reinforcement across all the perimeter of the building and also on the middle line of the building. Well, this building was prepared for carrying out 3 different tests, one in the corner column and another 2 in edge columns, as we are going to see in the following videos. Well, in this picture we can see the preparation of the test. In the top pictures we can see the foundations and also the precast of the elements that we carried out. And here on the top and the bottom pictures we can see the columns that are prepared for connecting them to the foundation, and also the columns with the corbels that are prepared for receiving the beams and for connecting the top reinforcement of the beams or the tying reinforcement through the columns, through each of the columns, just to provide the continuity, enough continuity to be able to resist the sudden removal of the columns. In this video, we can see the construction, the assembly of all the components. We started with the foundation, which was cast in place, and then we started with the assembly of the steel columns and the concrete columns. Okay. When we finished the assembly of the columns, we started with the beams and then with the hollow core slabs. like we can see now with the video. Finally, what we did is to pour the concrete on the slabs and also on the upper part of the beams. And in this video, we are going to see how was the first test. The first test was in a corner column, and again, there is a system with 3 hinges that only has to be destabilized, but only a little bit hit. So after losing the column, what we found is a very little vertical displacement of only 1.5 centimeters. We moved then to the other test. Well, in this second test, we did a test on an edge column, that received 3 beams from 2 directions. These 2 perimetral beams and this internal beam are joining together in this joint. So during the test, again, with a little hit here in the middle hinge, we destabilized the column, and the result was similar to the first one. We only found a vertical displacement of 1.5 centimeters. And finally, we did another test, the third one, the last one, it was last week, so it is quite recently. So what we did is to test an edge column, but in this case only perimetral beams had this frame, and in the perpendicular direction we can count only with the slab. So we can see now the video and how the test was done. In this case, instead of pushing the column with a machine, we pull the column with some steel bars. Well, and for the future, we, as Professor Jose Adam has told you this morning, we have the Enduro project, and in the framework of the Enduro project, in 1.5 years, we will test at full scale some sub-assemblies, and in 3 or 4 years, we will test 2 full-scale buildings, one made of concrete and one for steel. And we are going to move on the full-scale test we did on the steel truss bridge. Well, we had a unique opportunity because we have the railway, the Valencian Railway Agency is going to replace one of the buildings of its main line in Alicante. So we had the unique opportunity to take one of the spans, one of the static spans, to take it to the ICT laboratories. So with this opportunity, well, we had here in this video we see how the bridge was installed in the laboratory. We needed 2 cranes, one outside the laboratory and one inside the laboratory. So we can see in the video the outside crane that is installed there, and with the crane of the laboratory, with both, we can put the bridge on the side. Then this bridge was structural assessed by fatigue loads, but after the fatigue test, we did a robustness test, removing progressively the diagonal D1 and the diagonal D2. This test was carried out by a really big reaction frame, which was installed with an hydraulic jack, and this point load was distributed to 4 points during the test. So in the following video, we are going to see the final result after cutting these 2 diagonals by a saw. So in the video, we can see that after cutting these 2 diagonals, how the building is behaving under the loads of the hydraulic jack. So we can see that we have Pratt trusses in this kind of structure, but when we cut the diagonals, the bridge is behaving like a Beirinder beam. And as you know, although these joints are not prepared for resist flexural loads, in this case we needed to count with the flexural resistance of the joints just to resist the cutting or the failure or the disappearance of these 2 diagonals. We extended this work by computational models. Put the play in the videos. So, thank you, Lorenzo. And what we did is, well, extrapolating the results of the laboratory to another cases that are impossible to reproduce in the laboratory. For example, in this case, we can see the sudden removal of a bottom cord, as we saw in the first examples I did. All of these are being applied, all the recommendations we found and also the monitoring protocols are applying to 3 real case breaches with an spin-off company that is called Calsense, and they are monitoring these three breaches, these three steel breaches with a real-time monitoring. So what we are trying to do is to prevent some local failure just to avoid a progressive collapse on the structure. And this is the end of my presentation. Thank you very much for your attention.
So can we start with the next session? So let me introduce Professor Antoni Cladera. Antoni Cladera is a professor in construction engineering at the University of the Balearic Islands, and his research interests focus on the behavior of reinforced concrete and prestressed concrete structures, with special emphasis on shear strength and the external strengthening of existing structure using innovative materials, such as shape memory alloys. He teaches in the degree in building engineering, degree in agricultural engineering and the rural environment, and in the master in industrial engineering. He co-founded the YouTube teaching channel Ingenia, specialized in structural engineering, which has accumulated more than 1 million views. So, Tony, thank you very much for being here at the UPV, and the floor is yours.
Thank you very much. Okay, like this. Okay, so thank you very much for the kind invitation and for the presentation. And well, I was telling them that I feel a little bit an impostor here because I don't work on progressive collapse. I work with something much more gray, that is concrete, and much more boring, that is shear strength. Okay, but anyway, today I will try to explain our work in the last 10 years, I would say, and how following a line and believing that with mechanical models, you can arrive to understand your project and to find solutions that are useful at a given time, that can be interesting and can be a tool for other analysis in progressive collapse or other things. Well, okay, it is well known that shear strength causes problems in structural engineering, and here you can see three well-known collapses, at least here or in different parts. This is in the first one in Ohio. This is a very well-known and very studied collapse in 1955 that it boosted the research on the shear strength and the research on the size effect 10 or 20 years later. Here you can see a beam, a column that fell on shear due to an earthquake. And in Santander, this is a recent collapse 2 years ago of a slab due to shear punching or 2OA shear problem. So it is well known that shear can cause fragile collapses. And some years ago, we found out this text from Hugh Golder. He was a well-known professor in geotechnique and a consultant engineer. And for the first issue of the journal, of the geotechnique journal in 1958, he wrote down these words related to the earth pressure, Coulomb earth pressure formulation, but that is useful, I think, for any problem. It's a little bit long, but I think it's important to read it. There are two approaches to natural problem. There are the approach of the poor scientist and that of the engineer. I think that here most of us are engineers. The poor scientist is interested only in the truth, but for the engineer, on the other hand, there are many possible answers to a natural problem, all of which are compromises between the truth and time. So, and we should avoid forgetting this, okay? His answer, or her answer, was 60 years ago, must be sufficient for a given purpose. For this reason, an engineer must make assumptions, okay? We must remember this. Assumptions which, in some cases, he or she knows to be not strictly correct, okay? But which will enable him or her to arrive to an answer which is sufficient true for the immediate purpose. So, and the most important part, I think, is mistakes are not made when an engineer makes his assumption. Mistakes are made when other engineers forget the assumptions which have been made. For me, this is a text that I try to read every year to focus a little bit the research and to remember that we are looking for compromises between truth and time for a given purpose. And the given purpose will be very different when we are trying to design a new structure or when we are trying to study a structure that has any problem or when we are thinking in future progressive collapse. So we will have to adapt our models to the truth and time that we are interested in each time. With this in mind, and after having worked many years on this topic, this was maybe 10 years ago or more or less, two teams from UPC, from Professor Antonio Marí from Barcelona, and another one from University of Balearic Islands. We had been working for a while on the shear strength, and following a clear observation that is very, very basic, that is, okay, we have here the typical shear crack, and this is a neutral axis depth, and it's clearly divided into two branches. This is one steeper, and then here when it crosses the critical crack. And we had seen this many, many times in the lab, and also from people working on fracture mechanics, we found different papers that they also were studying this more from a theoretical point of view, and they say that the typical shear crack develops and it gets to the point A, that it will be here, more or less the neutral axis depth, and then it propagates here towards the compression zone, and here there is a clear redistribution of actions, but at the end, when the crack propagates here in the compression zone, the load practically doesn't increase. The load keeps more or less constant, and there is a redistribution, an internal redistribution of effects. So we decided to change a little bit what we had been done before. We were more used to work with models derived from the modified compression field theory, let's say, from Michael Collins, but then we decided to focus on to apply Kapfer's failure envelope, because you can work with principal stresses, and this is very useful and very well known by engineers. So here, what we are having here is not a fail due to compression or to tensile stresses, but to a combination of compressive stresses and tensile stresses. And with this in mind, and considering that the failure takes place when it fails the compression cord, we developed first with the people from Barcelona what we call the multi-action shear model. That was a model that has for the concrete contribution specific equations for the shear transfer in the compression zone, for the shear transfer across the crack by residual tensile stresses, and the Dowell effect, and of course the component of the stirrups. And from this model that was more or less complex, then we decided that very often we didn't have so much time, so the compromise between truth and time, we said, okay, as what we have observed is that main contribution is in the compression zone, let's simplify our model to what we call the compression core capacity model, that we are going to consider as the main action, and the responsible of the concrete contribution to the shear strength is only the shear transfer across the compression zone. I'm not going to present here boring equations, but this model, we found that it was useful for obtaining the shear strength of many different cases. We start with, in fact, we start with members reinforced longitudinally and or transversally with FRP. The original model was here because with FRP bars, they have a very reduced modulus of elasticity, so the crack width was very important, and in the test we could not see that aggregate interlock was that important at failure in those tests here with 1 to 3 millimeters of crack width. So we start here, but step by step we start working with reinforced concrete beam, without and with shear reinforcement, pre-stressed concrete beams, with rectangular T or I cross-section. For slender beams and for non-slender beams, we were able also to extend the model. For reinforced concrete members subjected to fatigue loads, for also two-way slabs or punching shear, for members with steel fiber reinforced concrete, and I will comment today a little bit of reinforced concrete beams externally strengthened with shell memory alloys, and reinforced concrete beams with corroded reinforcement. So a model that is able to work for many different conditions and that has been validated for more than 3,500 beam tests by all over the world by different researchers from databases made by other groups. Okay, we have also always used databases from other groups if possible, and so we saw that it's a robust model, and just at our university and many more at UPC, we have developed more than 160 tests of this test here. So it's a robust theoretical model, so we could try to apply it to many other things. And it also allows us to understanding the mechanics of the problem. In fact, when the model had already been developed, we were participating in discussions in committees and in ACI, the 445 committee, and also at European level. And okay, shear maybe is boring, but the committees dealing with shear, they are not boring because there are huge discussions there with people that say you are completely wrong, and they tell you, you are wrong. I think I'm not wrong because I have seen this. But then we say, okay, why? There is this discussion between people that says, no, shear strength, it's a matter of aggregate interlock or shear friction, and others, as Professor Park in South Korea, Robert Frost in the States, or we here in Europe, that believe that it's a matter of the compression cord. So 2 years ago, we say, okay, let's go to build 6 very simple beams, very simple beams. In fact, we did its test twice, so there were 3 beams just reinforced with 2 bars of 16 millimeters, or 2 of 12, or 2 of 10 millimeters. Very simple beams. And let's analyze with digital imaging correlation what is going on with the crack kinematics and with the shear friction. This was made really later after development of the model. And what we did, and this work was developed by, in fact, all this analytical part by Luis Montoya, that is a postdoc student in our group. And what he did is, when we had all the images from the test, then we went to the very last picture. Let's say, okay, this is going to be the critical shear crack. We are going to divide it. We are going to discretize this crack. And for each segment, we are going to study 2 points that at the beginning were very close. At the beginning of the test, they were just 1 millimeter one to each other. And then they are going to move during the test, and we are going to study the sliding and the crack opening. And we are going to apply the nonlinear equations or nonlinear model, let's say, by Walraven of aggregate interlock. So we did it for every second of the test. The tests were last for 1 hour each test, more or less, or a little bit more than 1 hour, or a little less. So every second we took the picture and we analyzed with with this model, with a lot of dig and MATLAB, for sure. And this is the results that we obtained for one test that it's more or less very similar to all the others. In this beam, you can see here the relative shear force. One is the maximum shear force. Okay, this is the relative shear force during the test. Here you have the seconds, and for every second we have performed this analysis. And you can see here different stages. For example, this is when what is going to become the critical shear crack appears. That is more or less here in this graph. Then the stage 1A, that we define it when the first branch of the critical crack fully develops, let's say until more or less here. And then for the maximum load. And studying the sliding and the crack opening and applying the nonlinear model by Walraven, what we saw is that when this crack fully develops and just it starts the second branch here in the compression zone, and this is the stage 1A. In this state, we have 90% of the load. In some tests, it was 94, 96% of the load. And the aggregate interlock, or shear friction, can only explain 15% of the shear transfer in this beam. Okay, so as the two main, there is an international agreement that the two main components are the compression zone, or for these beams, or the aggregate interlock. For 90%, you cannot explain, for 90% of the load, you cannot explain the shear strength transference through aggregate interlock, but it has to be at the shear transfer here in the upper part of the beam, in the top part of the beam, that is the compression zone. But then, suddenly, you can see here in this graph, for less than 10% of the total load, there is a redistribution, an important redistribution, and just for failure, the aggregate interlock in this beam represents 85% of this is just the step before failure, then it represents 85% of the shear transfer. So at the end, what we saw is that, okay, we have been discussing for 10 years, and we are discussing if we take the picture 10% before of the load, or 10% after of the load. This is all that we are discussing. But what we saw, here you can see, this is for 90% of the load. Here you can see the movement of the crack, here in green. This is for the 90%. And what we think as engineers, that for us it's much easier to focus here the analysis for 90% of the load and perform here and use here the equilibrium equations that are very common for all structural engineers or mechanical engineers, than to go to 100% of the load and to work with compatibility equations, anti-sliding, and things that are much more complicated from a rational basis. So at the end, what we saw from this dig analysis is that both models at the end are right, and it's just a matter of the photogram, let's say, of the picture that you are considering. For example, here there is an issue of Concrete International that is devoted to 6 different models. One is, our model is also here in this issue, and you can find the model by Benz and Collins that is based on aggregate interlock, or the model by Park that it's based on equilibrium on the top part of the crack here. And always the discussion is, you are right, no, I'm not right, you are right. No, we are both right, and it's a matter of a redistribution just before the crack. Okay, so with this, we think, or we were quite okay. We think that we understand the shear strength, and it's very important to, at least in our opinion, to try to confine the compression, the top of the beam, because generating compression stresses at the top, then you can delay the propagation of the second branch of the critical crack. And so we made this funny material. This is a shape memory alloy that you can deform it, and when you hit it, it goes back to the original position. You can see it again here. You have the spring. Okay, you deform even more, and it goes back. So, okay, this is a quite expensive nickel, titanium, niobium shame memory alloy, but 10 years ago, in the market, they start to produce iron-based shame memory alloys they are expensive, but not so expensive as this material. It's not so spectacular, but it's cheaper, so that's good for us, for sure. And what happens here is that when we have originally the spring or the actuator like this, the internal phase is in austenite, okay, and this atom here is neighbor of this B and C. And when we deform, we are not yielding the material, but these atoms here continue to be a neighbor of C. We are just displacing the connections, the atomic connections, and so when you give heat, you can go back, not only mechanically, but also heating the material, you can go back to this shape. This would be impossible if we have yielding there, because the connection would have jumped to the other atom, but this way it's always possible to go back. So with this idea, we start strengthening beams, not buildings, not big beams at the beginning. We start with conceptually with the same material of the springs here, with spirals or pseudo spirals, then with U shapes, and then we start working with iron-based shame memory alloys. You can see here also small beams with strips. We can say that it's a kind of inox steel with some nano additions, okay, this material. And then finally, we start working with more real scale beams, so we scale up the research, and we saw that it works. But because what we are doing, this is not only adding steel, let's say, for the shear strengthening, but also generating from the very beginning compressive stresses that will help us. What is the key of the material? Here you can see in a beam, this one was the original material that was very expensive. Then we moved to the other one, and it is like this, but when you hit it, it was to go back to the original position. We had pre-strained it before, so the material, you can buy it that it's pre-strained. So you place it, and when you hit it, you can see that it gets perfectly straight, because it's training to shorten, but it can't. It can because it's fixed, so it develops internal recovery stresses, what we call recovery stresses. This is the same in the Zwick press, and here is what you see, in fact, in a beam. And you generate internal stresses, not very high, but similar to what a normal steel will have if it had been placed in the beam at the really beginning, of the order of 300, 350, maybe 400 stresses. Okay, so what we are doing here, this is with Athena, you can see here that we are generating these compressive stresses that will help us to control the development of the second branch of the critical crack. And for service, when you place this material for strengthening, what you are doing is that for service loads, you cannot pre-stress normally a shear strengthening material, because the geometry is very complex. So for service limit states, the normal stirrups will not practically work. But as you generate the compressive stresses at the very beginning, the material works from the very beginning, and at the end, okay, you get to more or less the same failure load, but for service load, you control much better the damage in your beams. And this material, I know that it's, for many people, maybe it's the first time that they listen that it exists, but I asked last week to the company that starts this production in Europe, and they have developed more than 160 real strengthening projects in Europe, more than 160, but I can say that in countries that they have a little bit more of money than us, okay, because it's not a cheap material, but for strengthening of existing structures, the cost of the material, it's relative, okay, because what you have is your real building or your real bridge, and you want to protect it, and you can save a lot of money with a little bit of material. So most of projects you can see that has been developed in Switzerland, 120 big projects and 30 small projects, real projects. This is not research. Here, this is real strengthening projects. So it's there, and maybe it's going to become more popular in next year. And just to finish my presentation, but also with this line of shear strength, and thinking about strengthening and about the evaluation of existing, the assessment of existing structures, nowadays corrosion is for sure a problem, a real problem in many existing structures, and it is well known that what steel corrosion causes, the consequences, and of course the stirrups corrosion, because they are small in diameter and they have a reduced concrete cover, more reduced than longitudinal reinforcement, will affect the shear strength. And so we start trying to apply also our model to this problem, always thinking in this compromise between truth and time. So we decided to just focus on the most important effects that the corrosion has on a beam working on flexural with bending moment and shear forces. So we consider the remaining area of the stirrups only. Also for the longitudinal reinforcement, the remaining area after the loss of the cross section, and also we consider the spalling of the concrete in the web width. Okay, we reduce the web width to consider the spalling of the concrete according to a model that was on the existing literature. So you can see here there are, I don't know, around 60-70 slender beams with affected by corrosion. Here you have the cross-sectional loss ratio of the stirrups from 0% to almost 100%. And if we apply our model without considering corrosion, these black rhombuses, of course, would obtain very unsafe results for highly corroded beams, but only considering these three small corrections, that is to consider only the remaining area and to see if the concrete cover can spall, then like this the results are much better, of course, with high variability, because the corrosion problem it has this variability, but with a very simple procedure without almost time consuming, you can have and correct very well. So from there, what we are working right now is to try to conduct long-term predictions. So we know that it works for beam test in the lab. So right now we are saying, okay, let's apply our model, that it's a structural model, with material deterioration models, taking into account the carbonation of the concrete and also the action of chlorides in the steel. So you can see here, this is a beam subjected to carbonation here. This is carbonation, and here it's just at the sea front. And so we are studying right now the long-term reduction of the shear strength to be able not to perform or to plan the strengthening of the structures at the long term, but to think what will happen in 50 or 60 years in the future, because due to corrosion you can change from a ductile flexural failure to a fragile shear failure. So it's important to consider the evolution of this. So this is the end of my presentation, and just to conclude, of course, structural failure may initiate due to different causes, that's for sure. We have been working only on the shear strength, but we think that models that may be useful for designing may not work properly for understanding real failures. So And it's not a problem to work with different models when you are in front of different scenarios and different problems. But even some models that may look contradictory, they may look contradictory, but it's important to understand the assumptions, and all they can be valid, and if they are based in different assumptions, and you know which are the assumptions that are behind the models. Well, we think that we have been working in a robust model that work in front of very different circumstances that we have tested, and we think that it should work in front also of others that we are still working on them. And long-term predictions could be necessary to consider stirrups corrosion, thinking in increasing the lifespan of the existing structures. And last, iron-based shimmer alloys are a real alternative right now that they are already in the European market for strengthening existing structures. And that's all. Thank you very much. No, that's very important. Sorry, that was not all. I have been presenting this in 20 minutes, but this is not my work. This is the work just in this presentation. What I have commented in strictly this presentation, this is the work of more than 12 people in the different steps that I have been presented, and indirectly with researchers from this university, in fact from UPV, from EMPA in Switzerland, Refer, that it's a company producing these materials, and researchers from other universities. And without their work, this has been impossible, and of course, without the funds. Now, this is all. Thank you.
So, thank you very much, Professor Cladera. Well, I think that a friendly presentation on a tough task, sheer strength. So, thank you very much. Thank you very much. So, it's time for the next presentation. So, Professor Luca Pelà, are you ready? Yeah. So let me introduce Professor Luca Pelà. Luca Pelà is associate professor at the Technical University of Catalonia, and his research activity focuses on the seismic analysis of masonry structures and conservation of heritage buildings through a multidisciplinary perspective, including advanced computational modeling in situ and laboratory experimental tests, structural health monitoring, and new solutions for repair and retrofit. He has participated in more than 40 projects and is currently the scientific coordinator of 2 research projects with a total worth over 1.4 million euros. So the floor is yours. Thank you very much.
Thank you very much, Professor José Adam. Thank you very much, everyone. There is some problem with my presentation we are going to fix right now. See?
Which one is?
The drop.
Renato, I sent you the presentation by email. Sí, pero no me deja. It doesn't work. Okay.
Here I am. Okay. So, was a pleasure. It's a pleasure to be here in Valencia after some years. Last time I had the pleasure to be here at the ICITEC, and I'm very grateful for this invitation to Professor José Adam, to the Building Resilient Research team. Today I will be talking about a project we have been carrying out for the last 3 years. It's a project called Severus, started in 2019, is about to finish. It's funded by the Spanish Ministry of Science, Innovation and the University, the State Research Agency, and the European Regional Development Fund, which I gratefully acknowledge. It's a project in which we got, as you will see later, so many results, and all the papers related to the project are available in open access in the UPC repository for the science production, future.upc.edu. There are the journal papers, the congresses, articles, and the PhD thesis like that of Nirvan or Makonda, who is here. You can find all the results there. Let me start mentioning some of the most important results of the projects. The projects contributed to develop a methodology for a taxonomy of representative building typologies in urban environments, contributions to the development of laboratory and in situ techniques for the no destructive testing and minor destructive testing of existing masonry buildings. Also contributed to automated data analysis for structural monitoring of masonry structures, experimental analysis of retrofit techniques for the reduction of the seismic vulnerability of buildings. We contributed also with novel computational methods for the seismic analysis of masonry structures, and we finally did seismic vulnerability assessment at the urban scale, considering two real case studies, the city of Valparaíso in Chile and a neighborhood of the city of Barcelona. Why these two case studies? Because both case studies show a high seismic risk, but in a different way, because in Valparaíso the seismic hazard is high, but the seismic vulnerability of buildings is low to moderate. And on the opposite, in Barcelona, the seismic hazard is low to moderate, but the seismic vulnerability of buildings, for various reasons, can be pretty high. So, which is the motivation of working on seismic vulnerability of urban buildings? First of all, our existing urban centers show to have a very low resilience in case of earthquakes, with a high number of collapses of structures, casualties, socioeconomic losses, loss of operation of the vital infrastructures, and also damage or loss of the built cultural heritage, the main field of research of our research group at UPC. So the seismic risk assessment at the urban scale starts with the quantification of the seismic hazard, followed by the identification of the most exposed elements, and then vulnerability assessment of the buildings in order to have damage estimation, loss estimation, allowing to define mitigation plans and mitigation strategies to enhance the resilience of the city. So in the project we focused mainly on the vulnerability assessment, and according to the state of the art in the field, there are two main families of methods. One of them is the family of analytical methods, the so-called direct methods. They are methods in which we develop a rigorous analysis, structural analysis, for instance, using the well-known finite element method of each individual building. But this is extremely expensive, because we cannot do rigorous analysis of all the buildings of an urban environment. For that reason, we need an alternative approach, less precise, but more feasible from the resource point of view. And so there are some methods, like the empirical methods, that were developed during the last decades. These are also called indirect methods, and these methods allow the users, the analysts, the architects and engineers to make assessment of buildings with in a more speculative manner, less accurate, but in order to make feasible this and sustainable this work. One of them is the vulnerability index method. It's a method developed in the 80s in Italy, and this method is based on a large survey of post-earthquake damage in buildings after earthquakes in Italy. And so the method consists in identifying some different vulnerability parameters related with the vulnerability of the buildings. For instance, there are parameters about the specific characteristics of the resisting system, the types of floors, regularity in planning, elevation, and so on. And so the vulnerability index is the weighted sum of all the scores related to all these parameters. So the central point of the method is the calibration of these scores of the classes of each parameters from A, less vulnerable, to D, more vulnerable, and the weights of these parameters. So the method is really easy to understand. Any architect or engineer using his expert judgment can assign classes to specific characteristics of the buildings and then make this easy evaluation in a very fast manner. In the last years, some authors have further developed the method, improved and adapted to different built environments, and there is one of these contributions by these authors who added 5 additional parameters in order to take into account the effect of the building aggregate that is important in case of historical centers. Okay, so the methodology we followed had mainly 2 stages. The first one was the data collection, and it's really a challenging stage in which you have to collect all the necessary input data to feed your models. We need to make pre-filled activities or survey or desk survey, for instance, checking if the local archives have the original documents about the buildings, the original plans, the original information about the construction site when the buildings were built. Then we have to complement this information that is usually fragmentary with on-field survey by in situ inspection of the buildings. And then we have to manage the big amount of data, process them in order to finally have a taxonomy of the buildings, of the center we are investigating. All this data are necessary to feed our models. We wanted to develop a seismic vulnerability assessment by a hybrid method. Hybrid method means that the method, the outcome, the final product of the process is a vulnerability index form, like that produced by the Italian colleagues in the 80s, so with very simple classes, scores, and weights to assign to the buildings, but weighting all and calibrating all these parameters based on rigorous numerical analysis. This is something necessary in countries where, luckily enough, we didn't have recent earthquakes like in Spain. So since we cannot have a large database of large-scale observations of damage survey after the earthquake, like in Italy, we needed to simulate somehow the possible effect of an earthquake on the built environment. So the central task is to calibrate these numerical models very carefully in order to get realistic results. Then we have to analyze the representative typologies of the built environment. We have to make sensitivity analysis of the vulnerability parameters. We have then to propose our seismic vulnerability indexes and finally perform the larger assessment at the urban scale. So the first case study was far away from the UPC, our university, from Barcelona. It was the city of Valparaíso in Chile. We took advantage of having a PhD candidate from that city, Belén Jiménez. And it's a beautiful city, UNESCO World Heritage Site since the 2003. It's a city that experienced a fast growth in the 19th century because it was the major airport of the South America and the Pacific Ocean before the construction of the Panama Channel. And so it experienced a fast growth of the construction. The structural system is mainly based on timber frames, so light structures that can be assembled on site very fast. In fact, the structural components were brought from Europe and assembled on site. You have here some historical documents showing how the houses were sold in that period. So what we did was to make a survey from the local archives. It was really difficult because the information was fragmentary, many buildings without any record, all the documents, the few documents available, I must say, they were in paper format, and so you needed to make a visit and then desk survey in person. For that reason, the PhD candidate Belén Jiménez did an excellent work. She collected a lot of information there in our city, and also she did many inspection in situ of buildings, especially those under refurbishment works. And we noticed that the data you can collect are so much that you need some protocol, some working protocol to gather and to manage all the data. For that reason, we developed the building survey forms in order to have for each specific typology, for instance, masonry, concrete, mixed iron, concrete, or timber frame, all the required data for the seismic vulnerability assessment. Okay, so the timber frames in Valparaiso are really nice because they have these vertical posts with diagonal stiffening elements, and they are filled with adobe blocks, so unfired clay units. They are called adobillo in Chile, and especially for the exterior walls. While for the interior, we can have either blocks of adobe or this solution with boards, little boards of timber filled with mud. This typology of timber frames is called platform frame because the posts are not continuous from the foundation to the roof. They are a kind of modular floor system, no? So the posts are interrupted at the level of the timber floors. Here you can see some details of the beautifully executed carpentry joints, perfectly carved by the workmanship at that time. We made a taxonomy of the buildings by dividing them in families according to the structural systems, and we noticed that the 70% of the buildings we investigated were based on timber frame and masonry typologies. We selected two zones to investigate. Two selected strategic routes. These are evacuation routes in case of a tsunami. So in case of tsunami, people are gathered in the two squares and must evacuate through these specific routes. So following a recent concept, that is the concept of the emergency limit condition, this is a kind of limit state framework applied at the urban environment. What we want is that in case of an emergency, like the aftermath of an earthquake or a tsunami, we want to the buildings to maintain these roads to maintain their functionality, to allow people to evacuate. So we need that the buildings don't collapse. To calibrate our models, unfortunately, we didn't have any good and nice experiment on specific Valparaiso's timber frames typology. So for that reason, we had to consider just the experiments available in the literature. We did a comprehensive analysis of the available research literature, and we found out some typologies like the Portuguese ones and the Peruvian ones that have some analogies with the Chilean timber frames typology. So we used them as the unique reference available to calibrate our numerical models. So the numerical models were based on a lumped plasticity approach. Lumped plasticity means that we use beam elements and we lump the nonlinear behavior at the ends of the beam by inserting specific and very simple elements like rotational springs and axial springs with nonlinear behavior. So we calibrate all these components by considering all the tests for different types of carpentry joints, alp-lap, connection by contact, mortise and tenon, and until getting a good agreement between the experiments and the numerical model. After that, we developed our models. We selected some buildings that were kind of representative of the built environment, and then little by little we introduced to these reference buildings, we introduced some variation based on our past observation, both during the desk survey or on site. So, for instance, we consider the possibility of having one masonry wall or two masonry walls combined with the timber frame, something occurring in Valparaiso because these walls are commonly used as fire walls in the buildings. And this was a parameter, distribution of resisting system, parameter that is important in the seismic vulnerability assessment. Another parameter was the analysis of the regularity in elevation, because there are some buildings with some galleries or with a part of the facade that is cantilevered. Then we analyze the type of floor, so the different types of floors from light to weight, and state of conservation of the timber, of the connections, of both, by artificially decreasing the properties of the materials. And then we did numerous numerical analysis on the different models we developed, and we analyzed the range of variations of the results according for each parameter or structural characteristic represented by the model. We quantified the effect or quantified the vulnerability by considering this term, the mechanical index, mechanical vulnerability index, that is the ratio between the seismic demand on the building according to the site of Valparaiso over the ultimate displacement of the model. So we could quantify it for the different parameters. You can see an example of them. And finally, this allowed us to calibrate a new vulnerability index form for hybrid timber masonry buildings of the city of Valparaiso. So with parameters, new parameters, with a set of new parameters compared with the Italian works of the 80s, new specific parameters for these typologies. And we developed the fast seismic vulnerability assessment along the two strategic roadways that I have just commented, in order to identify those buildings that would require some more in-depth inspection, investigation, on-site survey, and perhaps some experimental tests, in order to increase the level of knowledge, and if necessary, even to make some intervention or strengthening to mitigate the seismic vulnerability. Then I would like to talk about the second case study of the project, the Eixample district of Barcelona. The Eixample means enlargement, extension is a Catalan word, and this neighborhood is the extension of the ancient city of Barcelona, the historical city center that is located here. So it's a neighborhood built in the 19th century until the early 20th century, was characterized by very fast growing and development, and today it's a neighborhood. I think it's the most populated neighborhood in Spain, with so many people working there. So the level of exposition is very high, because the neighborhood is organized according to streets, grid of streets with very compact blocks, and all the buildings located on the perimeter, along the perimeter of the block. The block is called Illa, kind of island. Island is the meaning of Illa in English. So the buildings built between the 1860 till 1940 are of masonry. So the built heritage is mainly of masonry for the 70%. And after 1930 emerged reinforced concrete typologies. We focused on masonry typology. So this is a building, an example of a building with load-bearing masonry walls. There are also typologies with load-bearing walls over, masonry walls over a frame made of steel or reinforced concrete at the ground floor. And this is the example of a corner building. So we made a building taxonomy. We identified some specific features of the buildings of this neighborhood. We also did analysis of the historical plans from local archives. We asked the help also of a colleague of us from the School of Architecture, having so many data from inspections of buildings. So we classified the buildings according to position of the stairs, shape, architectural configuration of the spaces, and we even plotted some histograms in order to understand which were the most important and repetitive typologies. We did also a very important experimental activity in masonry structures. Masonry is a material that is very challenging to reproduce with mathematical equations. Its constitutive laws are always very difficult to determine due to its composite character, heterogeneity, lack of standardization, depending mainly on the local construction habits. So for that reason, we needed experimental activities to define the mechanical parameters of the material. We did the in-situ testing during the project in some buildings, and we complete a kind of database based also on past experimental tests made by our group in Barcelona in the last 10 years. So we did tests on site by extracting small core samples that we brought later to the laboratory, and then we tested to get, for instance, the compressive strength. Then on site we also used some minor destructive techniques based on different types of penetrometers or pull-out devices in order to assess the properties of the components and the mortar. But we couldn't analyze one of the most important parameters in masonry, like in concrete as well, that is the shear strength. So for that reason, we had to replicate in our laboratory a masonry wall using some materials that were similar to those found in the neighborhood of the Eixample. It was really challenging to replicate the masonry because it's not easy nowadays to find a brick with low strength and handmade. So we did a thorough search of all these the available units until we got one handmade with low strength, and also we needed to weaken the mortar in order to reproduce the real ones. No, something that is exactly the opposite of what people are looking for, not to increase the strength and the performance of materials. We do quite the opposite in our research. So we added some limestone filler, recycled limestone filler to the mortar to a commercial premixed hydraulic lime-based mortar in order to decrease the properties. And so we built walls of 1.3 meters with a depth of 0.3 meters, so double leaf walls. We tested it we tested the walls under diagonal compression tests, and we did other tests, compressive tests. We did also non-destructive tests in order to relate the properties we got from the laboratory from controlled materials with those observed on site. And this way we could get meaningful input parameters for our numerical models. Here you can see some of them. are models based on very common shell elements, continuum finite element approach. You can see here a sample of the generation of the models with of a representative building with 3 patios, 5, 2, different number of stories, different types of floors. Also, we took into account a phenomenon very frequent in the Eixample neighborhood, that is the vertical extension. During the years, the buildings experience the rising of the height of the building by adding additional floors on top, or even with the staggered layout, and this of course is not that good from the seismic point of view because you are adding mass on top of the building. And then we also analyzed the hybrid building with metallic structure at ground floor, so there is a strong irregularity in height. So we try to reproduce as much as possible the possible variations and the possible characteristics of the built environment in a high number of models. We noticed that the most of models failed due to the shear failure, so diagonal cracking, diagonal tensile cracking at the base piers of the ground floor. This occurred both for the analysis in the X direction and the Y direction. We did the pushover analysis, non-linear static analysis, in which we apply the gravitational forces and then we push horizontally against the structure until bringing it to the failure. And also in the Y direction we notice the same type of mechanism, so diagonal cracking due to shear. We analyzed also the hybrid buildings and we saw that this irregularity at the ground floor, so this sudden change of stiffness in the elevation, can decrease remarkably the seismic capacity of the buildings. We also analyzed, it's very slow, maybe you can help me. Okay, so here you can see other examples of the results of the study of the effect of the historical vertical extensions, the so-called remuntas in Catalan. So we can see that from the original building without extensions, by adding progressively vertical extensions, we can reduce even by half the capacity of the building. And finally, we could propose vulnerability index forms specific for this neighborhood with a set of new parameters from 1 to 7 with the new classes, new weights. We kept 2 parameters from the original formulation of the model from the 80s about the vulnerability related to non-structural elements, because it can be considered pretty similar, and the general maintenance condition. And then we consider also the parameters related to the aggregate effect, and we are now in the process of analyzing the vulnerability index for a set of building. I will show you which parameters we are investigating. The first one is the seismic coefficient. This is the only calculation we are asking to end users, so to make a very fast evaluation of the capacity of the building compared with its own weight. The seismic coefficient, according to Benedetti and Petrini, is the ratio between a kind of overall ultimate shear that the structure can resist, and according to the well-known Tursen and Karpovich formula for diagonal cracking of the masonry walls over the total weight of the building. And then all the other parameters are very easy to assess, like kind of in number of floors, for instance, class A for a low-rise building up to D in case of high-rise buildings, horizontal diaphragms from rigid diaphragms class A until class D for very flexible diaphragms, plan configuration from compact to very slender configuration, presence of patios when it is centered or not symmetrical from A to D, vertical irregularities, so the presence of these vertical extensions, and the percentage of facade openings at the ground floor. And now we are in the stage, right now, in these weeks, in the stage of applying it to a selected neighborhood of the Eixample district. So we have selected that area, and an area in which the masonry buildings is the prevailing system. We are starting with this block made of 17 buildings, 16 made of masonry. The average construction year of the block is 1887, so they are pretty old. There are even very nice heritage buildings in the block. And we are currently asking to an architect to fill the scores, so to fill the form, to assign the score using her expert judgment. And so we are asking end users to fill the forms, and we are receiving right now the results, and we will then plot seismic vulnerability maps like we did in the city of Valparaiso in order to detect which are the buildings with higher seismic vulnerability, and so requiring further studies and possible intervention. Then the next step will be plotting seismic max in the current state and after a possible mitigation strategy. So among all the possibilities, we focused on a specific vulnerability mitigation strategy that consists in retrofitting the masonry walls with textile reinforced mortar, the TRM. For that reason, in our laboratory, we wanted to analyze which was the effect of this intervention on the walls. We built walls with the same properties that we have identified before for the constituents, for the handmade units, for the lime and weakened mortar joints. And then we applied externally basalt textile reinforced mortar, a continuous mesh of basalt textile reinforced mortar. Then we tried another layout using a steel textile reinforced mortar in the form of vertical and horizontal strips. This is a more time demanding and cost demanding solution. And then, since the Eixample presents lots of heritage structures, we had to think about a possible solution for heritage buildings with facades with exposed bricks, because we don't want to affect the aesthetical appearance of the facades of the buildings. For that reason, we invented a layout, this asymmetric, because on one side, on the exposed side, we have helical rebars near surface mounted, so it's a so-called joint repointing. So the bar is hidden, it's embedded inside the mortar joint, and then in the other side we put the basalt mesh of TRM. Of course, we dimensioned both, and we calculated the two reinforcement in order to get a rather symmetric, quite symmetric response at the two of the two reinforcement systems. For instance, the helical rebars, we put them every 3 courses of mortar. And we did the diagonal compression tests on the walls, and we noticed that from the unreinforced configuration characterized by a very brittle behavior with a discrete crack crossing the elements and splitting the specimens into two, and going through the mortar joints and splitting the bricks, we can obtain more ductile mechanisms. For instance, in case of basalt TRM, we could observe the cracking of the masonry substrate, but also a diffuse cracking of the mortar matrix until reaching the rupture of the basalt yarns. So a progressive failure with a very ductile failure, and very good from the seismic point of view. For steel TRM, the failure was different due to the higher strength of the steel. What we observed was mainly the delamination of the steel TRM from the surface of the bonding, and in many places. And about the near surface mounted helical rebars, we could notice that the cracking is not is not discrete anymore, but is diffused along the diagonal of the wall. So that's also good from a seismic point of view. Here is a brief summary of the results, and we can see that compared with the unreinforced masonry configurations, we can, with the basalt TRM, the steel TRM, and the joint repointing, we can observe a gain in the capacity from 100% with basalt till 31% for joint repointing, and as for the ductility, from 46% with basalt to more than 100% for the joint repointing. And the good news is that the tensile strength of the material we replicated in the laboratory had the tensile strength due to shear was 0.2 megapascals. With these solutions we can increase the value of these materials, and these materials is really important in our building, since the diagonal cracking, tensile cracking due to shear, it's the most frequent mechanism according to the calculation we carried out. We then repeated the tests on the same walls, but with a different type of tests. We did tests on wall of 1.3, 0.3 and 0.3 depth, but with a different loading pattern, so cyclic shear compression. So we did the tests for basalt TRM reinforced walls, for steel textile reinforced mortar walls, and so these results allowed us to get more information about the behavior of these strengthened masonry walls, not only in terms of capacity, but also in terms of hysteretic dissipation, energy dissipation. So these are the results for the basalt. We can see the capability of the material to dissipate more energy during the cyclic loading, and these are the results for the steel textile reinforced mortar. So now we are facing with the final tasks of the project. We will try to include in our models the effect of this mitigation strategy in order to improve the assessment of the vulnerability before the intervention, after the intervention, and making some proposals for the retrofit of the built stock of the neighborhood. The TRM systems have shown to improve the shear capacity, enhance the ductile behavior of the walls. It's a good intervention from our point of view because it does not alter either the initial stiffness, this is something we found out from the experiments, and more important, the mass. The mass is not increased because they are extremely light, so it's a very light intervention. And we could also investigate a novel reinforcement pattern with near surface mounted bars that is good for masonry facades with exposed bricks, so it's good for heritage buildings like those in the case study. And finally, since we got new values for the tensile strength due to shear mechanism, we will be able to improve the class of the building. So now it would be a matter to redo some of the analysis, of the numerical analysis, improve the evaluation, and make damage probability matrices before and after the intervention in order to suggest also to the public authorities some possible policies for risk mitigation. So here are the references. I have mentioned all the people involved in this project, the PhD candidates, our colleagues at UPC who contributed and are contributing to the project. I thank you very much for your attention, and I invite you, if you want to join the research, if you want to contribute somehow, do some collaboration. As you've seen, we have so many data to process, to analyze, and any collaboration will be welcome. Thank you.
Thank you very much, Professor Pelà. Well, considering that we are short of time, I will propose that we have the debate afterwards, okay. So we can move to the next presentation. Okay.
Okay.
Do you agree, Professor Pelà? Do you agree with the proposal?
Yeah,
Okay, thank you very much.
We can speak it later, don't worry.
Yeah. So our next speaker. So Jason Ingham is a professor of structural engineering and head of the Department of Civil Engineering and Environmental Engineering at the University of Auckland. And he is a past president and life member of the Structural Engineering Society of New Zealand and a fellow of the New Zealand Society of Earthquake Engineering. Jason's interests span concrete and masonry building and concrete materials technology, but he's probably best known for his research related to the seismic assessment and improvement of clay brick and reinforced masonry buildings. Jason, thank you very much.
Thank you, Jose. I wanted to start by repeating things that have already been said. I feel like I'm the biggest imposter of all the imposters, and there's several people here that feel like they're imposters apparently. I've never even thought about progressive collapse before the last few days, right? It's nothing I've thought about, it's nothing I've studied, it's nothing I even wanted to study. Jose contacted me and said, would you like to come to Valencia? And I said, well, of course I would. But what do I have to do, you know? So he said, well, we'll talk on something. So we decided that I would somehow try to weave together information on what was happening in New Zealand that might have some relevance to the research team and to your community. So this is a very odd presentation, odd for me and probably a little bit odd for you. And it's almost none of my own work. So I was originally going to put everyone's credit on every single slide, and I gave up and I thought I can't be bothered. So they're all listed across the front here. Des Bull is a very senior academic at the University of Canterbury and also one of the best known New Zealand professional engineers. Rick and Nick are both my former PhD students who have really gone on to quite great things in New Zealand. And Charles and Pierre are colleagues of mine in my department at my university. So I just really wanted to say here up the front that all the credit goes to these people and not to me. Now, I also decided this morning I wasn't going to practice what I was going to tell you. I was just going to make it up as I went along. And I was going to wait to hear what everyone else said in front of me and try to weave all of their stuff in with my own. So this will be a challenge about whether I can make it work. That didn't go forward, did it? Try again. There we go. Okay. So the first thing is, I can't get past asking this question about the seismic context. And you probably understand why. I had to go off and find Spain, which I thought, awesome. You guys must feel so proud. You end up right in the very middle of the whole ground. You know, it's wonderful. You're right slap dab in the middle. You know, and I looked at this long and hard, and it's like, okay, so look at all these white bits, right? So on the scale, if you're not familiar with this chart, 0 seismicity and huge over on this side. So there's lots of white, like in Africa, and I guess up in Russia, which is why I haven't seen many Russians, I guess, at conferences. But, you know, you guys are yellow and green and a little bit, you know, yellow's getting middle-ish. It's not 0, is it, you know? So it's like, oh, okay. So apparently Valencia's here. I had to go look on the map. So I started learning a little bit about Spanish geography. Well, I'm over here, right? Look at this. We're all red and brown. We're way down here in this color. So if you are only thinking about the green and the yellow and the white, you might find that there's not much that I have to share with you that's of any great interest. But nevertheless, I think the seismic setting is important because Jose has explained to me that this is supposed to be a study with a very international context. So let's go. That didn't work again. Try again. Okay. What do I usually do? Well, for about the last decade, I've been doing work a little bit like Luca's work. I think Luca maybe does do better work than I do. Looking at his slides, they look far better than mine. What this is pictures that I took as I walked out of the centre of Christchurch after the Christchurch earthquake. So I happened to be more or less right on top of the epicentre of the Christchurch earthquake. So there's not many researchers, I think, that can actually say they've experienced their own, you know, event, their 1 in 15,000 year event. But over the last decade or so, I have been focusing on how buildings collapse. And it's like, okay, well, that's kind of what we're doing here, right? How buildings collapse. So that's on the right page. So this is the work I do, and this is the last slide you're going to see of my work. And you'll be aware, probably, at least some of you, that a lot of this is taken out of European work anyway. So I steal a lot of my ideas from all the awesome things happening here in Europe. Okay, so then I actually Jose sent me his documents, and I read them, and I was confused, and I wrote all these notes in the margin. It's like, what does this even mean? And I'd like, did he even think about this? You know, do you guys do this too when you're reviewing someone else's work? Is this guy an idiot or what? What's going on here, you know? It's like, no, I know he's not an idiot, so he must have had something going on in his mind. So I looked at all these pictures, and I thought this one's a good representation, right? So it's been used several times. It's actually on the back cover of our little notebook here, right? And I was focusing on the diaphragms, and diaphragms have come up a little bit today. I thought actually, Luca, you might have mentioned them a little bit more than you did. For masonry buildings, they're very important too, right? Box-like behavior and everything else. And the lighting's not great, but there's all these dangling things down, and I can't really tell what the dangling stuff is. But I thought maybe it's the rebar. You know, so as these diaphragms are collapsing, they must be all ripping apart, right? It must be just a mess. So did the rebar debond? Did it fracture? I mean, how do you control all of this down here? Most of this is the diaphragms, right? It's not the beams and it's not the columns. But when I read the proposal, it's like, oh, we're going to put a fuse in the beam. And I'm like, yeah, well, the beam's like this tiny little piece. What about all the concrete in the diaphragm? So that got me thinking that I would probably try to weave a presentation around concrete diaphragms, having never tested a concrete diaphragm. Now, Rick, my close colleague, former student, lovely guy, he had a different presentation, and he sent me his slides, and I read through it, and I thought, oh, that's a good little line, I'll steal that. Too many people think about structural performance instead of building performance. And what he's sort of thinking about that is we analyze a beam column frame, right, and we wiggle it forward, and oh, we got a plastic hinge, and da-da-da. And you're not thinking about the diaphragms and the walls, and then you've got the non-structural elements as well. So I thought I'd leave that with you because I feel like the documentation we received was really, it was either silent or nearly silent on diaphragms, which I think are hugely important and tend to be forgotten a little. Didn't work again. There we go. Okay, so then Des Bull from the University of Canterbury has been doing quite a lot of work on diaphragms from a long time. And if this is sort of the basics, but just to remind you, I think too many people think that the whole point of a floor, you know, so you can walk around on it. And they forget about the fact that in an earthquake, the diaphragm's what keeps the whole building together. So here's our earthquake. This is like I'm teaching undergraduate students here, sorry, but here's all our mass. And it's got some sort of load, and then the supports are coming through from the reactions. And the loads are somehow being transmitted through the diaphragm with sort of compression arches, right? So it's like a deep beam tipped sideways. And I got a little schematic there in the 3D if you're completely confused what we're looking about. But the diaphragms sort of serve this role that I think we tend to forget because it's a big chunk of concrete, and as long as it doesn't crack, no one asks too many questions. So this is the slide this morning when I was thinking about what we did yesterday, and it's like, you know, the really difficult thing about all of this is, well, where are the compression struts going? And you got loading in two directions, so they've got to turn around, but they've also got to get around the voids. And that's when I said, oh, you guys cheated with your building we went and looked yesterday. We had to climb up the scaffolding outside. You didn't have any voids. So anyway, but not only that, you know, the earthquake doesn't just go this way or this way. It goes in all sorts of different directions. So the load paths have to be able to handle the entire 360 degrees. And that's why I really liked what Uwe said in his first presentation, that, you know, one way is to think about alternative load paths, or the other way was to think about segmentation. I thought that was great, and I'd try to weave that back in. Because I already knew I had this is, well, where are all the loads going through the diaphragms? And if you're thinking about putting some fuses, well, how are you going to put your fuses in that still make sure this still works? Well, I know what everyone says. It's like, oh, yeah, but we're in Spain. We don't have earthquakes, so it doesn't matter. But, you know, that's cheating a little bit, unless you decide you're going to do a project with no earthquakes. Okay, so it transpires, as Bing mentioned, that a very senior colleague of mine at the University of Auckland many years ago, and his name is Richard Fennick, did some work that really received very little international attention, but that when beams cycle backwards and forwards, they don't close back up. The cracks keep opening on both sides. And what that actually means is that the building during the earthquake, as it rocks, gets wider and wider. Not at the ground, because that stays the same, And what you eventually have is the potential for the floor to fall right out through the middle. Now, apparently, when they've tried to publish some of their work internationally, the international peer reviewers have said that's silly, that doesn't happen. And so a lot of this work never really got international attention. But here's the idea of a hollow core floor plank. And we asked this question yesterday on the construction site. Well, do the planks span one span or two? Depending on how close your columns are, the plank may span across two bays. But it doesn't really matter whether it's one or it's two. Anyway, because of the elongation of the plastic hinges, you have the potential for the perimeter frame to move outwards and the floors to fall through. Now, initially, this was a hypothetical concern. We had done single plastic hinges. We had measured how long the plastic hinges worked. I became involved in some of this work early in my career, helping Richard Fenwick finish off various projects. It was certainly his idea, not mine. Then down at the University of Canterbury, they built a full-scale rig about 15 years ago, roughly. And they shook it backwards and forwards, and they had the floor plank fall out. It's like, oh, it really can be shown in the laboratory. But at this point, it was just a lab invention, basically. The problem is hollow core is used all over the world, right? Including all over Spain, I now know too. So you guys should be paying some attention. Keep pointing at the computer like you told me. Right. Okay, so this was a brand new building in Wellington, our capital city, on the waterfront area with reclaimed soils, and we had an earthquake and a lot of shaking. And you can see, lovely, modern, glass, fancy, went through the earthquake, and from the outside, looked fine. But when you look through the window, the floor had fallen and out, right? Now, the earthquake happened at night. And so the floors all fell down and no one was killed. But it's like, this building was only like 3 or 4 years old or something, right? Brand new, owned by the government. And so here again, you can sort of see stuff. So this was the first time it had actually been proven. Now, Kaikoura, I wondered about putting in a graph, and now I wish I had. Kaikoura is several hundred kilometers, that's the epicenter, away from Wellington. But the shaking transmitted several hundred kilometers and caused this collapse. So the reason I haven't had any money for masonry research lately is because all the concrete guys got a huge amount of money for diaphragm research. And so this has been a real focus of attention and why I've stolen everyone's slides. Point at the computer. Okay, now I'm jumping backwards again. If you're new to timeline, I'm having to tell a story and then jump back. After they had established about 15 years ago that the hollow core can fall through, the guys at University of Canterbury in particular said, well, we need an alternative solution so that when the beam hinges, it doesn't grow in length, so it doesn't push the frames apart. And so that was the idea that we need to be able to put a gap in here so that we can still get plastic hinging without having to get it walking. So they came up with this detail because one of the things Jose said was, we'd like to see how you guys go from concept research to actual practical implementation. And this was a successful project where consulting professional engineers were responsible for designing or commenting on the test rig with the idea that if it was proven in the lab, it would get used in the field. And this is where Des Bull and his company, Holmes Consulting, got involved. So here now you can see the full rebar details, and they were precast units. And so I'm just stealing some of the stuff and I put the credits in too. None of this work is my own. And it worked. It wasn't hugely successful because people thought that's an awful lot of effort to go to. What we also did then is we have a very straight line of communication between the researchers at the universities and the National Code Committee. One of the advantages of a little country is basically it's not that hard to get on the code committee and write the code, whereas from what I can gather in Spain it's hugely complicated and not even broad, just too hard. Anyway, so not only that, we were able to change details. So for instance, now our recommendation, if using hollow core, is to put a gap in here. So this gets sacrificial so that you got some a gap between the deformation of what the hollow core is going through versus the frame beside it. Still not working. Okay. So then this is again the laboratory at the University of Canterbury, and again you can see full-scale construction with a lot of support from industry. Does this actually work? And it did. And what we saw, and again another theme, is if you're trying to introduce new ideas to the professional community, there is nothing quite like having a crisis event like a huge earthquake to have everyone prepared for the first time to try new ideas. One of the things Jose and I were discussing the other day, and I completely agree, is that we are in an extremely conservative industry, and they are not really usually very interested in trying anything too new. But after everything they've been doing has failed, all of a sudden they're interested in trying new stuff. So this just happened to be a bunch of buildings that have been built in Christchurch since that have implemented some of this new technology. But coming back to that comment from Rick, point at the computer, there's a difference between structural performance and building performance. So what then happened is over the last few years, there's a big Q here. This stands for Quake Core, which is a national centre of research excellence, which really has all our universities working together, which is why it might seem a little unusual that a guy from Auckland's talking about the research from Canterbury, but we all work this together. This is actually a project now done as a joint New Zealand-China experiment, Tongji University in China. Anyway, and they put this thing through full-scale shake table testing, the whole huge works, right? So this in itself is a keynote presentation that runs for 45 minutes and everything. But the point is they went back and they retested all these details again now, full building performance. The only thing that's different is they put a little damper device under here to help dissipate some energy. But otherwise there's that rocking pin detail that we showed you earlier. And it worked. They managed to avoid any of the floor failure at all, right? So no damage now, no issues around beam elongation, no cracking of the hollow core, no collapse, nothing. Big tick. Excellent. Now it's not working. Point straight at it. There we go. What we're looking at here, this slide would have made use if I'd had about 10 minutes ago. Here's a conventional reinforced concrete beam column and joint. So that's the idea. Cracking, 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 cracking. Cracking's getting bigger. And what you have is this is beam elongation here. So as this thing cycles backwards and forwards, you just measure the beam slowly getting longer and longer. But if you put that other detail in, instead of like 25 millimeters of increased length, you get this idea, well, yeah, 1 millimeter or something, but otherwise no problem. So it worked. Excellent. Still not working. It's like it needs 2 clicks every time. There we go. So this is stolen straight out of Rick's slides. The new technology now has been really well validated. So I imagine this is the same thing you see all over the world, but certainly in New Zealand we often see that products get used before they're really fully properly tested. And the first time they really get tested is like in the earthquake, and then the earthquake proves that they didn't work as well as people thought they would. And then we all go back years later and test them, knowing now we've got this huge issue that we've got an entire stock of buildings built that way that actually don't work as well as we hope they did. But also keep thinking about those interactions during the design. That's why I highlighted that line in red, because I keep coming back work packet 2 and all those fuses you're supposed to come up with, right? There's going to be a lot of complexity around these fuses and how you're going to be trying to design for your avoidance of progressive collapse. That's going to have a lot of second order impacts, I think, especially if you try to put earthquakes into the story. And the other one, which you may or may not buy into, because presumably if you're doing fuses, you might have to start using some gadgety devices. But be a bit careful about, you know, all these things. So we've got people, must happen here too, everyone wants to sell you an energy dissipator or a base isolator or this, that, or the other thing. There's a whole lot of technology that you can kind of buy in catalogs now to help. But the idea is make sure you understand the basics. So as I was sitting there in New Zealand, I was thinking, well, maybe maybe the guys in Spain don't care about any of this because maybe they have cast in situ floors. So if you've got a reinforced concrete cast in situ floor, then I think a lot of what I was going to talk about didn't make any sense. So it was only when I got here on Monday and said to Jose, well, do you guys use hollow core? And he goes, yeah, we use it all the time. I said, oh, right, perfect. So your hollow core and our hollow core is pretty much identical from what I can tell, right? Just tubes. How do you build it? You stick it on a ledge, right? You reinforce the topping. Yes, just like I got told yesterday at our construction site. The section itself is basically unreinforced except for it's pre-stressed. You know, the webs between the voids, quite narrow. And this stuff just breaks right off, either under what negative bending or positive bending. It doesn't really matter because depending on how well you've got your topping reinforced, you can break it either way. So at home, hollow core over the last, say, 5 years has basically become like the dodo, extinct, right? I'm trying to weave together all my conversations from there. I'm looking at Nervin from Mauritius because he was wearing a dodo t-shirt the other day. So we're not using hollow core anymore because we think it's too seismically vulnerable. It's too brittle. Instead, what's taken off is, I should have put this in the slides, profiled metal decking with a reinforced concrete topping. So it's still like a precast solution of some sort. So the most recent work, again, is now a big national collaboration. This photo's taken at the University of Canterbury, but half the people in here are from the University of Auckland. This is Professor Ken Elwood, if you know him. So he's the leader of this project, but also funded and endorsed by all the sort of the big players. National government has put some money in, local government, both the universities, and Branch is this Building Research Association. So again, one of those themes, I think, that if you've got all the parties that are going to be wanting to implement the results at the end of the project, being part of the project design from the beginning, then they're more receptive to seeing the results. So this project, the most recent one, and these slides are only now a few months old, is again a full-scale test, but this time to figure out what we're going to do with all the existing buildings in New Zealand that have hollow core in them. And so this is a retrofit project now. And the idea that they looked at, the one on the right, this is looking, well, basically underneath, looking up, is to use strong backs, and the other one is to use like a catch frame. And I've got better pictures coming. So the idea with the strong backs is to somehow say, well, if this thing wants to break off the support, how do we put stiffeners in here to help catch it? And that's what it looks like. Fair bit of work if you have to do that to every floor and every building, you know, up and down the country. It's going to be a hell of a lot of work. But the alternative is you're going to have to knock your building down. And this is the other system, which is the idea of essentially turning this into a sort of a whole truss structure sort of thing, which in my mind, you only have to look at for a moment and say, that's a hell of a lot of work. And do people want that on their roof? So I was quite pleased when I noticed that everyone else agreed with me that the favoured solution really is the strong backs. So now there's a nationally endorsed technique for how to retrofit your hollow core floors in existing buildings. And the idea with these standardized solutions is to then knock down the design fees and have contractors being able to do standardized solutions to drop down the cost as much as possible so that you can actually start doing this quite effectively. Now, so that's the hollow core story, that's the diaphragm story. Just to weave in a few other things that I thought could be useful. We've heard already today this project's going to have both concrete frame and steel frame. So Charles Clifton from our university has been doing this work for well over a decade, maybe 15 years now, on a friction slip arrangement for steel that relies on friction. These are slotted bolt holes, and so it's all about bolting or having enough force across the bolts and then relying on the coefficients of frictions of different steel shims and different arrangements, and then to have this be able to slide and hinge in two directions. So it's really a steel solution of the same idea, in my mind at least, as what you saw for concrete. So Charles, who's a member of staff at my university, before this had worked for the National Steel Organization that put out the steel design codes, and that's called HERA, Heavy Engineering Research Association. So they endorsed his work and put out a national guideline for how to use it. And then our biggest structural engineering company in New Zealand, several different engineering firms, have taken it on board and developed it further, such as with like a steel circular tube, concrete filled steel tube, and other sorts of things. This detail has now been used in over $1 billion worth of buildings. I think that's interesting. That's the way Charles likes to talk about it. It's like, okay, $1 billion. How many buildings is that? How much is a building worth? I'm not sure. I don't know how many buildings it is. He just likes to say, yeah, my detail's now in $1 billion worth of buildings. So it has been adopted by industry, and it's very popular. It hasn't yet, as a detail, been put through a major earthquake, but it's received a lot of attention. Anyway, we'll leave it at that. The only other detail I wanted to share with you guys, again, is this idea of fusing of a sort. Tectonis is a spin-off company from my university. It's really hard to see in the lighting here. There's some guys underneath here. This is just a screen capture off their website. But they've developed a system. What you're looking at here is timber column. This is actually an airport, a regional airport, and timber frame structure. And it's kind of like a knuckle system. So what you're looking at is some springs squeezing together, and then these things kind of like consuming energy as they ride over each other. And so this is their Tectonis detail, and so that becomes a rocking column where this thing kind of rocks and opens out with energy being consumed as it rocks backwards and forwards. And so there they are being used as diagonal braces, and they've been used also in both steel buildings and in concrete buildings as well. So I just wanted to close out with some basics, but just because it went through my head as I read all the paperwork, I thought I'd chuck it in. That I do think in terms of fuses or controlling some sort of progressive collapse or such thing, there is a lot to be gained by making sure you understand some basic principles of earthquake engineering around regularity and how you might split your building, and the fact that a lot of that tech already exists. So I've just stolen a couple of pictures here of some rather basic stuff, and then I went roaming around trying to figure out, in my head it's like, yeah, but it's already common practice to break complex buildings into simpler bits. And I found this picture of an airport, and I don't know if you can make out the red lines, but it's just showing you that this already has a number of movement or isolation joints in it. And then as soon as you just sort of like search for isolation joints on the internet, you find loads and loads of pictures. So that's all existing technology. I just keep wondering what that means for sort of seismic load paths trying to cross these joints. Also, as I was reading the proposal, I kept coming back to the fact that it seemed to me there's quite a lot that could be learned from bridges. And so again, I was really quite pleased when Uwe started off this morning with the Confederation Bridge, and I thought, yeah, that's what I thought too. You know, some good lessons from the bridge community that could go into this today. So I've had a little bit of exposure to the idea of integral versus non-integral bridge abutments, and then the idea of long span bridges with their expansion joints and other such things as fuses, just throwing in some ideas. And then I was even thinking about, you know, reinforced concrete pavements and some of the details there around dowel details and such things, because we're going to have to think about how to fuse our diaphragms. So I thought, well, maybe, you know, there's quite a lot that's been done already in the world of concrete. So this is kind of a wrap-up. First point, having been here a couple of days and talked to many of you already, I think there's sort of like a bifurcation right there at the very beginning. Is there a seismic context to this problem or not? And if there is, then you instantly face a whole family of new questions compared to the fact, okay, we're in a place where we don't have earthquakes, so we can just forget that question entirely. I think that is so much easier than what I'm talking about over on this other side here, where it's like you've got to think about a lot of stuff at the same time. I do think even if this is not a seismic project, there is a huge amount of learning that can be taken from all that really expensive seismic validation testing from around the world that you can probably grab and use. I reckon that maybe you guys should be thinking about getting away from precast for this project, because if you're going to be putting some fuses into your diaphragms, then how the heck do you use precast units as well as using fuses at the same time? Either that, or you're just going to say that we're just going to let our precast planks fall on the ground and that's part of it all. So that's my thinking over the last couple of days. You're actually going to intentionally let them fall off their ledges, or what? In which case, maybe in the end, just build them out of cast in situ floors. This complexity, which I guess came up in Luca's presentation too, around that whole family from details to members to assemblages to the entire building performance as a system total. But I know that's already built into your work packages. And this is something I've stolen from Rick as well. And I think it's already in your project, but I love it as a phrase, the burden of proof. There are so many people, I think, that do a lot of structural validation using things like numerical modeling. It's like, yeah, but have you really proved it? It's like, yeah, I ran a finite element model. Yeah, but is that really proof? You know what I mean? So this phrase, the burden of proof, I think that's something to really think about. What have we done in New Zealand? Well, I think we have the advantage of a small, tight-knit community that actually it's just easier to make change. So we can't get around from that. You're actually part of the entire European Union. That's just much harder to force through change. But after the Canterbury earthquakes, people were so much more receptive. So much new technology got implemented that probably would never have been implemented otherwise. So, you know, that sort of starts leading to like, oh, you know, next time there's a big terrorist explosion, what do? You get over there somehow? You know, it gets a little bit confusing what you do out of that, but I think people are more receptive to new ideas after a disaster event. I think the phrase that we often use at home is co-design. If you can think about who's going to be using your results and get them to be on board at the beginning with a vested interest in the project from the very beginning, that makes a big difference. So just think that through. Point at the computer. Yeah, so coming back to that idea, get the practitioner community on board as early as you can, including co-funding and other such things. Also, from what I can tell, all the way from students to graduates to professionals, everybody loves worked examples and user guides and such things. So publish a bunch of user guides and worked examples. People seem to love that no matter where they are in their career point. I wanted to finish up by just saying thank you. Thank you to everybody. Thank you to Jose in particular. This is my first time overseas in 2.5 years. This is my first presentation to a real set of people. I've been presenting on Zoom, you know, for the last 2 years, so it's been just a pleasure. I keep coming back to the fact that I think it's, you know, source independent or source agnostic or whatever phrase you want to use. I really struggle with that. So, you know, don't ask why the column has collapsed. It's just collapsed. It's like, yeah, that doesn't work for me. I need to know why the column collapsed, because I think that helps to inform what sort of building it was, what sort of jurisdiction you were in, what quality control went into the construction. So I know I've mentioned this before, but I think that's that notion of scenarios. And by that, what I'm sort of talking about, well, if it is an explosion, then was it a terrorist explosion? Was it a government-owned building? Was it an embassy? What sort of architecture goes into that sort of a building? I think there's just this whole sequence of questions where they one follow to the next. And this idea of independently grabbing things is not actually real somehow. And then yesterday we were discussing, does this project even address bomb blast or not? That's a huge question to ask. And then when I thought about it, after I thought about everything else, I thought, you know, there's a big ethics issue here, I reckon. So if you're going to design a building so that basically we're going to put some fuses in here, that if something happens, that piece of the building can fall out, right? And you come to work, it's like, I'll have that desk instead of that desk, right? That's the one that's actually going to fall on the ground, and that's the one that's going to stay behind. I don't want to sit here. That one's been designed, I'll die. That one's been designed, I'll live. Isn't that a big ethics question?
Different price.
So I'll just leave that with you guys, because that's not my problem. But anyway, thank you very much. That's it.
So, Professor Ingham. So thank you very much, Jason. So
You're welcome.
very useful comments for the project, and we promise that in our intense debate tomorrow, we'll have our sponsor for you. But it's a challenge. So this afternoon we work very hard. So thank you very much. So you know that we're short of time. So if you agree, we can have the next presentation. Rico, are you ready? Yeah. So let me introduce Professor Rigoberto Burgueño. Rigoberto Burgueño is a professor and chair of the Department of Civil Engineering at Stony Brook University, and he received his PhD thesis degree in structural engineering from the University of California, San Diego, and his recent research focused on harnessing elastic instabilities for adaptive materials and structures and use of artificial intelligence for structural health monitoring. So thank you very much, Rigoberto.
Thank you, Jose. Good afternoon, everyone. I have the dreaded spot of having the presentation before lunch, so I'll try to stay within time, and let me start my timer and make sure that I keep my track of. I guess we have a competition here as to who's the most odd person out of this whole topic of being not a researcher on progressive collapse. I'm very appreciative of the invitation to be here again in Valencia, a place that I visited fortunately a few times, and every time I found something new to learn and something that impresses me. Wonderful to be here. It's difficult to follow that wonderful, great presentation from Jason, and especially when he warned you to be careful about, I forget now, but gimmicky devices, right? Which is exactly what I'm going to talk to you about. But Jason and I have known each other for many years, and he, from the time that we were in grad school, overlapped for a few years or for a year or so. He knows that I've been working on gimmicky stuff from the beginning, and he has been critical, and it has been very helpful to consider that criticism. So coming back to progressive collapse and my presentation, I told Jose the same thing. Well, I don't do this progressive collapse research. I've been doing this different work lately. And I did not try to address progressive collapse at all. I just presented, I'll share with you relatively recent research that we're still going on. And perhaps this is something that you find of interest, because within the context or within the spirit of this challenge that Jose is trying to tackle here with new concepts for controlling progressive collapse, requires innovative thinking and considering different ideas and ideas that are perhaps non-obvious. And perhaps within this context, you may consider the work that I'll share with you. So, conventional design of reinforced concrete shear walls are well known to all of you, and they rely on, in terms of seismic behavior, on the inelastic deformation actions that happen on the wall. And of course, they're well designed. We have inelastic actions that take place in our materials, concrete and steel, in order to dissipate energy due to hysteretic actions. Unfortunately, that could also lead to severe damage, and that is costly to repair, residual deformations, and special detailing such as boundary elements that may need to be provided. So we know the advantages that they can work well, as well as some of the disadvantages when these systems do not perform as adequately as we would like. Some solutions to this technology have been provided in the last 2 decades or so in the attempt to minimize damage. And this is an example of unbonded precast segmental walls. So these are unbonded post-tension shear walls in which the idea is to minimize damage by using precast segments provided with post-tension in tendons, where the energy dissipation is by means of rocking. However, the rocking mechanism itself does not provide sufficient hysteric energy dissipation, and these systems usually require the provision of coupling energy dissipation devices in order to provide the adequate response that we need. And there are many devices that have been provided for this purpose, whether they are metallic devices that yield, damping device, viscous dampers, or friction-based dampers. So there's a clear motivation to develop seismic resistant systems that are, damage-free, or that can be with reduced damage performance especially after moderate earthquake events. So the project that I would like to share with you is a new concept, a concept that we have termed pendulum shear walls. It's a concept in which the seismic resistance is provided by a precast post-tension wall, but in which the wall, instead of being on a flat interface at the wall footing connection, is gliding on top of a curved surface. And the opening, instead of an opening of a gap at the base, the wall actually glides on the surface, and that's the name pendulum, because it's a point of rotation. And the other interest is to make the system self-centering by the provision of energy dissipation devices that are self-centering and that can take advantage of the kinematics of this peculiar wall deformation mechanism. So the objectives of this peculiar research was to develop those structural systems capable of persisting extreme damage, extreme events, seismic events with no damage, implement performance metrics that allow us to achieve immediate occupancy with little or no damage, develop performance metrics that are not restricted by traditional material failure limit states, and implement energy dissipation devices that are capable of dissipating energy during repeated full range of motions, from low events to high seismic events. So these are the general objectives of the research. We're still working on this. So this is the, I start with some of the tasks that we're doing, we'll get right to it. So this is numerical simulations that we started doing to understand the behavior of this pendulum wall system, and this is just an overview of the finite element model. It's a three-dimensional model in which we are trying to evaluate, most importantly, the parameters such as the curvature of this circular arc at the interface, the post-tensioning level on the walls, and the frictional characteristics at the interface. We evaluated this in comparison to an experimental setup that we were considering with the collaborator, which is Pedro Franco Silva at the George Washington University. So we considered cyclic displacement pattern. So this is just an overview of the type of numerical modeling that we did in order to do some characterization studies on the system. So among the things that we have found that are interesting is that, for example, here we look at the top deflection of this single wall, and these are the different radiuses that we have considered. All these analyses were done with a coefficient of friction at the interface of 20%. And what is interesting is that this to be when the radius is very large, that means it's a flat wall. You have this type of deformation. These are different type of post-tensioning levels. That's the difference in the colors. But when the radius is very low, almost a circle, the wall really starts rocking like a pendulum, and the displacements increase. So there's a optimization. There's a minimum or an optimal level in which the deformations are minimized. So then we try to find what is the optimum radius for this wall to be sliding. So that's one of the first parameters that we have looked into. The other is the issue of the friction resistance, and here this is a little animation of the response of the system. I don't know if you can perceive the motion of this simulation with the rocking. So what you see is obviously some kind of a hysteretic response being captured by the simulation, and this is just due to the friction parameters, which depending on the level of post-tensioning force and the friction characteristics, you do end up having some level of energy dissipation. And we have been able to characterize the shape of this hysteretic response depending on the friction parameters. Of course, we would like to be able to experimentally validate these options. And as a first attempt, Pedro, George Washington, built a mock-up wall built out of wood just to evaluate this. So this is a wooden structure, a wooden single wall. This is the actual test unit here. And has the curved base, cyclically loaded with an actuator, post-tension in strands to provide the anchorage response. And here are some of the results. And he was able to change the friction coefficient at the interface by varying, by taking the wall apart and then varying these different conditions on the plates that interact between the two surfaces. On the left is the force deformation response of systems with high friction, in which if you have very high friction, you end up having uplift of the system, so it doesn't behave as sliding, and then you have similar to this rocking straight interfaces with very little energy dissipation. If you are able, if the system does behave in pendulum motion, then the energy dissipation due to friction does activate. Of course, there's questions and considerations as to what happens over time as these friction parameters will change and how will that parameters, how that behavior will change. Now, this is another series of experimental results with the analysis. So this is the analytical and experimental data. So that means that we're sort of able to capture the response. Of course, there's some dealing with friction is quite challenging. So we are not quite capturing the slopes, and it turns out that by using some very delicate, very precise measurements at the interface of the wall, the tangential stress distributions along the interface are not uniform. So that basically what we would define as a coefficient of friction is not constant along the entire surface, it changes. So that is very difficult to define in the numerical simulations. The other interesting thing is the variation of the axial force. This is the axial force in the post-tension in tendons. One of the limiting factors of the standard precast post-tension walls is that you must limit the amount of the post-tension in force. You must limit the gap opening, otherwise you may yield the post-tension in strands. This is the axial load in the wall, or on the strands as the wall was being deformed. The numerical simulation and the experiments do diverge, but in general, it varied between 34 and 26 skips, which is very, very small compared to the overall capacity of the strand. So we do not change the level of pre-stressing force because the wall is really gliding. Furthermore, I want to add that there were a total of about 8 or 12 experiments, I forget now, with the same wall that were repeated, taking it apart, changing the friction parameters, changing the axial load, and conducting another experiment, and there was absolutely no damage in the system. So this wall is just sliding there. Okay. The next step on the project, which is really what my main part of the effort is on the energy dissipators. And I mentioned that there are different solutions that are, there are tons more than these 3, but these are the main 3 categories by which all energy dissipators fall. We have viscous-based dampers, friction-based dampers, and yielding-based connectors. I'm sure you are familiar with all of them. You have this typical hysteretic response that allows the dissipation of energy. But for our application, we perceive that they have some limitations. Viscous dampers, they tend to be rate dependent. Friction-based dampers require high force of activation before they can be efficient, and they add a lot of stiffness. Metallic dampers have permanent deformations that will not allow for restoring systems. So we wanted to do something different, especially with this type of walls in which we were aiming at low damage or no damage systems. So what I've been working on for the last 10 or 15 years or so is, along with a large community of people, is trying to look at structural elastic instabilities as a welcome feature for the design of innovative materials and structures. So basically, there's a transition that has been happening over the last 10, 15 years in considering buckling or instability in an elastic stage as an actual beneficial feature in the design of materials and structures. So this is one of the classic papers that says, a perspective on the revival of structural instability with novel opportunities for function from bucklophobia to bucklephilia. So my latest research is trying to find ways in which we can use buckling to our advantage and instabilities. So which led me to so when we consider instabilities here, I'm referring to, there's two main kinds that we can consider. Buckling, which is the sudden loss of axial load bearing capacity by an element, or snapping or limit type equilibrium response. I'm going to be concentrating with snapping type behavior for this presentation, in which a system will have a transition, a limit point transition to an unstable branch, and find another position of equilibrium until it's able to carry load again. So this is a well-known classic mechanism, one that we generally try to avoid, but that, as I'll show you, and that we can use to our advantage. So this is just a simple Van Mises truss that shows the snapping mechanism. And I will use that as the illustrating mechanism for the design of these innovative energy dissipator concepts. So what happens is that when you start looking at instabilities, let me go back here. When you look at one instability, you load this Van Mises truss and you apply the load at the apex of this mechanism, a 3-hinge frame. So the load increases, you get instability, and you can load back. Now, once the system is in this position, it's said to be bistable, it cannot return unless you load upwards, all right? So that is well known. Now, what happens when we provide the system with a restoring mechanism, some kind of a restoring force, let's spring? So then the system changes from being bistable to be called monostable. So it will have the instability, but some strain energy will be accumulated in the spring that if you, upon removal of the load, the system will return. All right? So now the system will return, but there will be no energy dissipation. Now, if we connect two of these trusses in parallel, in which the deformation is the same for the degrees of freedom, we can increase the capacity of the force required to activate, and we have two elastic bifurcations, two snap-through events. And we can keep on doing this, all right, and connect many of them. Now, if we connect this element in series, something very interesting happens. So again, we have the Van Mises truss with the spring mechanism. So if I connect one, now what this spring mechanism does is that it makes our system go from the classical snap-through to be able to have a snap-back type response. And this allows us to be able to dissipate energy. When we connect systems like this in series, we have multiple bifurcations, but every time that you have a bifurcation, there's a vibration of the free degrees of freedom. And it turns out that if you have one system, you get no energy dissipation. You follow this curve right here. Okay, so you follow this curve. If you have two, you will snap once, you will snap twice, and you still get no energy dissipation. If I have the spring systems or something to store the strain energy, I'll have 1, 2 bifurcations, and it will snap back along exactly the same path with no energy dissipation. But once you have 3 or more, the story changes, right? Because you have a free degree of freedom that is allowed to oscillate. And this oscillation releases the kinetic energy, the strain energy transforms into kinetic energy, and you have energy dissipation. So now I have 3, 1, 2, 3, right? And when I remove the load, it will snap back 1, 2, 3, but this little blue shaded area is energy that was dissipated. So this is hysteric energy, but the system is elastic. There has been absolutely no damage. And if I connect more of these elements, all right, I will start having multiple bifurcations, and when they snap back to their original geometry, the area, of course, increases. In the limit, you get a response that is essentially elastoplastic if you have an infinite number of serially connected trusses. So how do we go here to our system? So we want to develop elements that show this type of bistable and monostable behavior. And one of those systems that we have developed is what we call a cosine curve dome. It's essentially a dome structure that has the cross-sectional profile of the first buckling mode of think of a fixed beam. You can work out the buckling mode for the first eigenvalue, and then you revolve it into a surface, and you can make these domes. And by changing the parameters of the span, the thickness, the modulus, etc., you can control their behavior. And just like the von Mises trusses, if I connect them in parallel, I can increase the load required to introduce the instability. And if I connect them in series, I can increase the number of bifurcations without exceeding the load. By using these two type of connections, I can control the amount of energy, the stiffness, and the force at which this system activates. So we did that, and we created what we call the multiple cosine curve dome, and this is my gadget, right? So this is my gadget, and so we can stack them. These little discs are actually two domes that are connected in this form in parallel to increase the load, but otherwise they're in series. And the idea is that we can modify or we can characterize the monostable response of a single dome, and then by controlling the arrangement in series and parallel, I can design the profile of the resulting force deformation response, which, as you can see, is very similar to what we would have for a self-centering, restoring, flag type, energy dissipating device. So where the area inside this response is our dissipated energy. So how does this look like? This is, again, some more schematics of the same device, a finite element simulation, and these are just two resulting responses that indicate that by controlling the design of our dome, I can change the area of this response. I can stay within the quadrant here, or I can go at the bottom. Now, if I cross the zero line, what that means is that my structure becomes bistable. It stays in that position until something pushes it back up. So I don't want that. I want to be up here so that it returns automatically by the stored strain energy in the system. So I need to make sure that my domes are monostable. So this is an experiment that we did on, these were 3D printed domes stacked in the multiple system. And can you play the video? So this is just I don't know, the idea here is that you can see that these domes are being pushed down, and then they are being actually loaded in both directions, tension and compression. And every time they snap, they will do the response, these little humps that you saw in the previous figures. So this is the result of the experiment. This is experimental data, and the blue and red lines are analytical responses, which I'll show you in a moment. But you can see that this is not a schematic. This is actual experimental data on that tested device. So this is another video that shows that we can do this bidirectional. So the response, this force deformation response, is the actual experimental data for this system. We configure it with some guiding rods and a platform so that the device works in bidirectional. So you can see that the platen is racing. So we can develop, little gizmos that do this kind of thing, and where we can control the shape of this area. So now to take this to the walls, we're going back to the walls. Doing the finite element models of these domes and so on is too complex, so we developed some analytical models that can simplify the response. So we can capture all this snap-through behavior as long as we can understand the behavior of the single dome. And these are just some of the key characteristics, the loading stiffness, the unstable path, and then the reloading stiffness. Then we can recreate the entire response by knowing how many of them are connected and so forth. And here you see a comparison between the experiment and the analytical model. So we can predict this with relative confidence. Now, the other interesting thing that I share with you is that this behavior is not rate dependent. It doesn't matter how fast or slow you test this, you get exactly the same result. because the response is essentially elastic, and there's no damage to the device, and it's again self-centering. So we evaluated the amount of damping that you get out of this device. This is the level of damping, the energy dissipation. And as you would expect, as the number of connectors increases to infinity, you can see that these little jagged zigzag lines, these little drops in load every time there's a snap-through event, they become smaller and smaller and smaller, eventually giving you an idealized type response as this one. So as the system, you can see that this is the increase in damping coefficient. As we get to about 10 units, we almost start getting close to our plateau in the amount of damping that we can dissipate. So it doesn't take a lot of them. So then we took this response to the wall system that I previously showed you. But we want to use these devices as the connecting elements of 2 of those walls. So in this case, we incorporated the connectors at 3 locations along the 2 walls being separated by a gap. Now, we subjected the walls to an earthquake record, and of course, this I think was the Northridge earthquake. And then to simplify matters, we simplified the response of the connector by this flag type response. And in order to introduce this into the final atonement program that we use Abacus, we modeled the connector by the assembly of 3 springs. So we connected a linear spring that provides the stiffness. We connected a nonlinear elastic connector to give us the activation load. And then we put in parallel an elastic perfectly plastic connector. By having this assembly of nonlinear springs, we can control the shape of this flag type behavior. So then we can introduce it into the 3-dimensional model with a little bit more economy into the simulation. So these are some of the results. And I guess the animation is going on. I don't know if you can perceive it. So in the top, this is the response history of the displacement at the top of this 2-wall assembly. The first line that I want to call to your attention is this blue dotted line, which is the response history of the single wall that tends to have a residual deformation depending on the amount of friction at that interface, right? If the friction is 0, it returns back to 0 displacement because the force in the cables and in the strands and the gliding restores the system. But when the friction increases, you end up having some residual deformation. Now, the use of the connectors, which is all these other different cases, and I'll tell you what they are in a moment. But you can see that in general, there can be a reduction of the displacement amplitude, and the system becomes self-centering. Now, we introduced we did different studies by changing the design of the connectors. You can see that we have 3 different flag type designs here, some that are weaker, and some that are much stiffer with more energy dissipation. And we're still not fully aware or fully comfortable with the results, but we do see differences, mostly because the stiffness of the system gets affected by the devices, and it has changed a little bit of the responses. But in general, we find that the response is very, very similar, and it just changes slightly on the amount of self-centering of the system. We're still characterizing this, but overall, we think that it has some very promising behavior, and it's doing what we expected as far as having a self-centering capability that is now provided to this interesting wall behavior. So now, as a whole, this system with the pendulum walls, with the elastic energy dissipators, is completely damage-free. Right, so the walls are gliding in these curved surfaces, the connectors are elastic, and they're dissipating energy. So the whole idea of having energy dissipation by means of elastic deformations sometimes is counterintuitive. I share with you very quickly that this dome design that I share with you is not the only one that we've been playing with. We've done other concepts that basically manifest the same type of instability. One of them is basically inclined beams. So you can have tilted beams that will snap through. You can imagine this beam, a fixed support here with a roller. You apply a load, and then eventually will have a snap-through response. So if we can arrange them in parallel, like in this column, I can increase the load. If I can arrange them in series, like the multiple columns, I can have multiple snaps, and then I can design my energy dissipation regime. This is I think it will play it. Can you click? This is an experiment on that concept. So again, it's rate independent, and it's elastic, and it's self-centering, and it's just a different concept that we have been exploring. And these devices can be incorporated in other systems. We are incorporated in these pendulum walls, but they can be used in other systems. And these are concepts that we, for example, a concept for a frame. And this, we did some preliminary studies in which we took a reinforced concrete frame, conventional design, the response due to an earthquake. And this was a Chile earthquake. This is the yielding of the rebar at the connection of the columns. So the conventional design will exceed yield in some locations. We provided these elastic energy dissipators by means of a chevron frame, and we were able to reduce the demands below the yielding. So in this case, it's a supplemental damping device to a conventional structure, but by means of an elastic energy dissipator. And so the dissipator doesn't have to be replaced, it's not damaged, it's not rate dependent. So with that, I reach some conclusions or a summary statements that I've shared with you a new concept for walls. It's a little bit awkward. There are many wrinkles to address constructability, connecting multiple stories, and so forth. But it's nonetheless, it has some interesting features that we think that show that this motion along this curved surface allows for some energy dissipation that is damage-free. The behavior can be characterized by the friction properties at that interface. We have been able to demonstrate that energy can be dissipated by taking advantage or harnessing the multiple elastic instabilities in systems for self-centering energy dissipating devices that are damage-free. We have developed this cosine curved dome device that we think can be implemented in these walls as well as other systems. And in terms of these pendulum walls, these connectors have allowed this system to basically behave with no damage and achieve self-centering capabilities. So I hope that you found this interesting. It's, again, non-ordinary, but perhaps sometimes solutions to problems require that we try to think differently. Even it takes us to uncharted paths. So with that, I want to acknowledge my collaborator, Dr. Silva, who is at George Washington University. He has been concentrating his work mostly on the walls, while I work on the energy dissipators. These are my former and current students who have contributed to different aspects of the work. And the funding for this research has been done by the U.S. National Science Foundation. So I appreciate all of this team effort. And with that, I thank you, Jose, for the invitation. Thank you all for your attention. And if you have any comments, or now or later. Thanks.
So thank you for Professor Burgueño for sharing with us your innovative ideas and creative projects. And well, this is an inspiration for us because you know that we want to move forward with our project. And well, this is a good example of innovative research. So thank you very much.
Thank you.
So I think that it's time for lunch. If you agree, we can meet again here in 1.5 hours at 3:30. Okay. So we can close this session and we'll be here again in a few minutes. Okay. Thank you very much. This break, we have our next presentation. You know that although we are in a slight delay, we'll finish the session. Okay.
12:45.
So, well, David Stevens is a principal engineer at Protection Engineering Consultants and works in the San Antonio, Texas office. David was managing principal of the company from 2016 to 2021 and has returned to technical work and business development. David has extensive experience in research and design for progressive collapse of structures and for weapons effects on structures and armored vehicles. So David, thank you very much for being in Valencia.
Well, thank you for the invitation, Dr. Adam. It has been a very enjoyable trip and an enjoyable workshop so far. So I'm looking forward to the rest of today and tomorrow. So again, my name is David Stevens, and I do know something about progressive collapse, so that maybe puts me ahead of a few people. Not very far though, but I do know a little bit. Dr. Adam asked me to spend a few words, or spend a few minutes, excuse me, talking about, so you should talking about my company. So that might have been a mistake on his part to say I could have a few minutes, because I do like talking about my company. I'm proud of what we've done and what we can do, but I will try to keep this short. On the other hand, we are a contractor, so we always market as whenever we get a chance to, and try to find interests in people who will fund us. So we're a small business. We're in Texas. We started in 2006. Two friends and I started the company then. We work in protective design, testing, assessment, and advanced analysis. Customers are U.S. government, global engineering firms, infrastructure owner, developers, and manufacturers. So geographically, that's where we are. We have two main offices in Texas. One's in Austin, the other is in San Antonio. And we have single employees working around the country now. Since COVID, lots of people want to work from home, and we've been flexible about that. So when we started the company, our main areas were research and testing, and then physical security, protective design. We still do quite a bit of that, and I'll show you some videos of some of the things we do. Lately, we've started working in data science and software development. AI and ML is the cool thing now, and so everybody's trying to get into it. This was a natural extension of a couple of projects that we had to develop those techniques, and then this turned into a really good business area, and we're continuing to grow that. And we've also, in the last couple of years, started to do assessments, mostly explosive safety assessments. So this is a project where we designed the buildings and the instrumentation and wrote the test plan, etc. for two. The building on the left has conventional glazing, the one on the right is hardened. The figures on the left there are actually numerical simulations. It is amazing what you can do with graphics tools nowadays to make those look realistic. But we do numerical simulations for close-in blast. The videos over here are of a half-scale bridge pier with an explosive close into it. Caused lots of local damage. This is a program that, or project, we work in progressive collapse. The video on the right, and could you play that, Lorenzo? It's not automatically starting. It was at the University of Texas at Austin, so they use water to cause the floor to collapse. They wanted to measure force versus deflection, and so they did up to the point where it collapsed. And this one, so we have a project with the Federal Railroad Administration looking at putting better safety hardware alongside trains or passenger trains. I think there was a case in Spain in 2005, 2006 where a passenger train went off a curve and some of the cars slammed into these catenary poles. That's what this guy is here. This is a test device for that. But these suspend the electrical power lines that the trains run off of. And if the train does derail and slides into those, right now they're fixed, and so the car crumples around it. The intention here is that the car will, or it'll shear off like common highway roadside safety devices. So the picture on the right, I guess it is going to show, is just pendulum testing to show that what we designed worked as well as it should. It was more technically challenging than you might think, given that we do this for highways all the time, but that's a story for another time. All right, so we also have looked at shock and dynamic effects on bolted connections and welded connections. So I don't know if I can play the one in the lower left or not. Can you play the lower left one, Lorenzo? So this is the actual test. And you can see the bolts popping, and then the simulations are there and there. So the agreement was really pleasing. The one thing that we really learned in this significance is that if you're going to model failure in steel, you need to include triaxiality effects. So if you could play that one, Lorenzo. Oh, is it going? Okay, yeah, there you go. So if you don't have triaxiality, if you just use the standard failure parameters, the standard material models, you get something unrealistic. If you include triaxiality, then you get the black shear tear out that one would expect. All right, so we do data science and engineering analytics. This is the only slide, but this one's really cool. And the young smart guy I work with developed a procedure using evolutionary genetic algorithms, and you create parents of possible solutions, and then you compete them and breed them, and then they create children, and then you go through the loop again. It's all very eugenic, if you will. It's a little creepy when you talk about it, but it's a great way to reach an optimized solution in a few minutes when it used to take a few weeks. All right, so we do conventional design for blasts. So these are some of the buildings that we've worked on around the United States. So we'll design them for blast threats and for physical security, and every once in a while for ballistics. We do facade design or glazing designs. This is a federal courthouse that we worked on before. One of the things that our skill set allows us to do a conventional building like this, but then when you discover the threat is such that there are no closed form solutions or any place to look it up, we can do numerical simulations and do them quickly. We've gotten very efficient at it. All right, so what time do you know what time I started, Jose?
Time.
Yeah, what time I started. I'm curious as to how much time I wasted. I feel a little guilty about doing marketing, but on the other hand, that's how little businesses survive and grow into big businesses. So anyway, thanks for sitting through that. So now we'll get to the reason why I'm here. So I do have a long history of progressive collapse design. I'm primary author for the U.S. Department of Defense Unified Facilities Criteria for design of buildings to resist progressive collapse. In the next number of slides, you'll hear UFC repeated a number of times, and if your memory's bad like mine, you'll start wondering what he's talking about. So this is Unified Facilities Criteria written by the Department of Defense. So as a primary author on that, I've been involved in the Disproportionate Collapse Technical Committee as the chairman, and then we're writing an alternative load path analysis guidelines at this point. And I'm also on the Standards Committee, and I was chairman of Chapter 5. So we're going to talk a bit about the Standards Committee and the standards that's getting pretty close to being released. All right, so in terms of history, a brief history. In the United States, there was no formal requirements for progressive collapse design prior to the Oklahoma bombing in 1995. So the British and then the Europeans, or Europe, took over or started up in 1968 when Ronan Point occurred. The U.S. never got on board with that. All we really did was put in some lightweight integrity requirements for steel and reinforced concrete, and we called that good. It was investigated, but nobody took the lead on actually implementing progressive collapse design into a standard. So after Oklahoma City, a colleague of mine was working for the DOD at that point. He wrote the first set of guidelines. It was 5 pages long. As you can guess, it was pretty terse and needed to be fleshed out. So the company I was working for at the time was hired to write the UFC, and I was chosen to do that. The first version came out in 2005. It was very flawed. It's embarrassing, and thankfully our sponsor recognized that it could be improved, and we received follow-on funding and then released a greatly improved version in 2009. However, note that it went from 5 pages to 245 pages. So we proved we wanted to provide value for the customer's money, so we gave them lots of guidance. All right, so just for you, I have heard UFC mentioned a few times. I'm not going to belabor this, but it did follow the British approach. So you have hardening, tie forces, and then alternative load path. We weren't recreating the wheel. We were taking what the British did and making use of it for DOD. All right. So it's thread independent. This is for Jason's benefit here. It surprised him when we talked about this yesterday. So if there is a known threat, if somebody tells me I've got a 500-pound bomb at 50 feet away from my building, I can design the building to withstand that. There's plenty of guidance for that. The DoD knows that, recognizes it, and that's what they hire people like us to do. But there are events where you don't know what the threat's going to be. Something unusual is going to happen. Maybe the terrorist is rude and decides to bring 600 pounds at 50 feet, and then you do get a failure. Or there's an internal gas explosion, or a truck bumps into a column. So there are lots of different ways that you can create collapse. And so the DoD decided they were going to finally develop guidance for it. They wanted to use the civilian guidance, but again, the civilian community in the United States had not done any work on that. So, all right. So yeah. So the alternative load path approaches in the UFC heavily relies on ASCE 41. If you haven't read that document, it is a wonderful treatise on structural engineering. You will be a smarter engineer after you get done with it. It also, you should read it just for your own edification, but it's just, we sold or used leveraged lots of it for the UFC. And the tie forces are based on catenary action after loss of a column or a load-bearing wall section. It really is a simplified or codified version of alternative load path. It's just, it was developed by taking columns or wall sections out of numerical models and seeing how they respond. So essentially was the alternative load path to develop those values. Yeah, it is warm in here, isn't it? Or I'm just getting overly excited, one or the other. So.
Sorry.
Yeah, well, I turned it down earlier, but the green light hadn't gone on. I wasn't sure, so thanks. Maybe by the end of this, I'll stop sweating. So anyway, so moving on now to the U.S. standard. So in 2009, 41 years after Ronan Point, the United States American Society of Civil Engineers, I left out civil, anyway, ASE decided maybe it was time that we get serious about progressive collapse in the United States. So the development of the standard, and this again is for civilian use, began in 2009. The first public ballot was just completed, and it'll probably be approved by late 2022, so by the end of this year. All right, it is performance-based, unlike the UFC and other approaches. It allows you to define your design requirements and allows you to define your acceptability, your acceptance criteria that shows that you've met your design requirements. It's a departure from what, it's a departure anyway, from typically what is done. In the United States, people are trying to move to performance-based codes. It's slowly being done, and this is one that is moving that way. There are a few people who objected to making that performance-based, and we'll talk about that in a second. All right, so there is no legal authority inherent in this standard, so it's going to be published and it'll be on the web and anybody can grab it and use it. It won't be actually put to use until a government agency or what they like to call authority having jurisdiction, a weird lawyer phrase, but anyway, an authority having jurisdiction has to require this being used. So the state of Florida might require that this has to be used from now on because of what happened at Surfside a year ago when the wing of the condominium collapsed. Or a county in Texas might decide they want to do it. But until somebody says legally you have to do it, it's just going to be there and not being enforced. How often will it be used? That's a good question. You know, the building industry in the United States is competitive as it is anywhere else in the world, and adding 1% to the cost of a building has to be justified. And it could be 5% to meet the requirements. So we'll see how often it actually gets used. But at least it'll be there, and if the state of Florida does decide to use it, then it's going to be ready to go. Interestingly, so speaking of Florida, 6 weeks ago there was a Structures Congress in the United States, and I was part of a panel discussion of the standard. There were 2 engineers there from Florida who were wondering if they could show that their buildings met the requirements of the SEI disproportionate collapse standard. Would they be eligible for insurance reductions? Because right now, all of the condominiums up and down the coasts of Florida and Georgia and Alabama, they're getting hit with huge insurance rate hikes because they settled for the Surfside building a month ago or so. It was $995 million for 94 people who passed away, so about $10 million a person. So anyway, we'll see how if it you know, people use it to get their insurance rates down, or if it's going to be you know, we'll see how often it's used. So these are the chapters. I'm not going to go through these in any detail. I did want to point out, I will go through a few of them. I did want to point out one of them. I wasn't, the chapter 2 definitions was heavily derived, if not directly taken, from Dr. Starossek's work. Mark Wagner, who is the chapter lead, mentions that every time he talks about it. So thank you, Dr. Starossek, for making it easier. The risk assessment, it's really a little bit different animal. Come on. There we go. All right, so the UFC, the DoD doesn't do risk assessments. They have a different perspective. They're mission-based, so what only matters to them is they accomplish their mission. And so they don't care necessarily about fatalities or necessarily about costs. They just have a job to get done. So they don't do risk assessment, but because the standard is performance-based, you go through a risk assessment procedure, which I'll talk about in a second. And so this standard, I'm not sure how many pages long it is, and I'm not going to go through it in any real detail like I just said. And even what I'm putting in here might be a little bit too much detail, but if anybody's read standards or you looked at the EN or the old BSI standards, you'll see how this correlates to it fairly well. So chapter 3 is risk assessment, and it's a conventional description. Well, there are lots of ways you can define risk, but the committee chose hazard likelihood times vulnerability times consequences. So if I have a rough building design, I have an idea of what the vulnerability is. You know, I have a concept. I know that I need to keep cars away from certain walls or certain columns. And I can figure out what the consequences are if it's going to collapse. I'm going to know there are 200 people in there and maybe they'll all pass away. One thing that is really hard to determine is hazard likelihood. And when we wrote the UFC, we realized that there's not a database you can draw from on progressive collapse events that say 1 in 500 years I'm going to have this occur, or 1 in 50,000 years. So we decided to make the UFC consequences based. You know, the military couldn't lose too many people or they wouldn't be able to perform their mission. But in the standard, we're doing this risk assessment. And these 3 values, hazard likelihood, vulnerability, consequences, they have ordinal rankings, and those are the ranges from there to there. And there's some guidance in the standard about how to come up with those. But the one thing that is, it has to be pointed out, this is all based on judgment. You're not going to find any hard numbers anywhere to do this from. And so we're all human beings and our judgments differ, and if I have one goal that's different than your goal, my assessment of risk might be different than yours is. So this is going to be highly qualitative here. After you do that calculation, you'll get these risk values here. The numbers go from 1 to 140. There are building categories depending on what they're used for and how many people are in there. And then you go into this table and you find that you have collapse resistant design category A or B or C or D. So CRDC is a new acronym. Doesn't exactly roll off the tongue, but I didn't come up with that. Most buildings are going to fall in lower areas where you aren't going to have to do a lot to get them working. So chapter 4 is the one after that. It defines the initiating events. That's one of the things I think we'll be talking about tomorrow relative to segmentation, is what sort of initiating events do you have. It also talks about performance objectives. So after you apply your initial damage, what's the performance of the structure that it has to meet to be considered acceptable? So this is a sketch of 2 of the 3 components that compose risk. This is consequence, this is probability. So you don't, for small damage, you don't want to have large consequence. This area is always unacceptable. And as you work your way down here in a performance sense, you get to the point where you design a building where it can have a large amount of damage, maybe 2 columns or 3 columns removed, and there'll be small consequences. So this notionally drove the requirements for the CRDCs and then the initiating hazard introduced in. Now sometimes it wants to work really fast. Maybe it's getting warmed up in my sweaty hand here. The come on. All right. So there are 4 hazard independent damage scenarios. So again, these are the initial or initiating events. And I'm not going to bore you by going through 4 of them. I picked the second one, H2, so it's the second most severe. So it's defined one of 2 ways. And, one is that there's damage to an individual secondary member. So you might have a bracing element that gets pulled out, and that's considered your HIDS 2. But what's sort of novel is that Mark Wagner, who also wrote this one, decided that you could use a notional cubic damage volume, in this case 2 feet by 2 feet by 2 feet, and then you move it around and you see if the damage occurs there and you lose that part, is the structure going to collapse or not. That concept came out of the Swedish building codes, and initially that's what we had, the only thing we had in there, but a lot of people didn't like that, so we went back to defining the removal of individual secondary members. The next level up is removal of a individual primary member. But I'm not going to bore you by going through all those. So this is a performance-based standard, so you're allowed to have different responses to your structure. So you might decide that having a failure of a single component is not acceptable, or you might decide it's okay to have part of the building fall down. A partial collapse is okay because there aren't going to be any people in that area, or you're willing to accept the risk for that. So there's a full range, a full gamut there. The amount of collapse that's allowed is determined by what's called the area of influence, which is similar to live load reduction in the U.S. code, but it's the area of influence as defined as the loaded area over which the influence surface for structural effects associated with a particular structural element is significantly different from 0. And then there's an example in the UFC about how you do that. All right, so performance criteria, as I just mentioned, you can have a whole range. You can say that there are components that can't fail, some that can fail. The area of influence for the components that fail, you don't want to have too many of those. And then you're allowed to have partial collapse, which is a departure from what the U.S. has done before. But you know, you don't get anything for free. So, all right, there you go. So the bottom bullets that just flew up. So partial collapse is incredibly hard. Well, partial collapse implies that the debris are falling down. They're going to be landing on the floor below and driving collapse again after that. So that is very hard to calculate or predict. The floors don't magically get separated at their ends and drop down flat and land flat on the floor below there. The rebar pulls out or the bolts gradually fail, the beam tilts, the floor tilts, it slows down, you know, as the rebar is trying to hold it up. There's no easy way to do that, so my chapter 5 was supposed to address that, but we realized quickly that the state of the art is beyond that, or it's beyond the state of the art. So we put in there that if you're going to allow partial collapse, it's up to the designer to prove that you can have partial collapse and not let that grow into progressive or complete collapse. If you do that, then you're going to have a third-party reviewer because it's going to be a very difficult and very involved analysis. All right, so the chapter 5 is the one that I was responsible for, design and analysis approaches. It's essentially taken straight from the UFC. Unfortunately, it does not allow tie forces or hardening. It is only alternative load path. So the alternative load path comes out of the UFC. Pretty much all the analysis will be based on that. You can do linear static, nonlinear dynamic. There are 2 other approaches. One's called alternative rational analysis. So we wanted to leave in the possibility that people come up with new approaches or new methods or new structural configurations, and they weren't prohibited from using them because the standard doesn't is restricted to only what's in there. So if you're really smart and you have a new method, then you can propose that and get it approved, but you have to have a third-party review. And then there's some deemed to comply solutions. So there are times when, you know, if you have a HIDS 1 and you have to take out a volume that includes bolts, and you have a bolted connection that's got 16 bolts in there, you don't have to take each one out and decide whether it's going to fail or not. You can look at it and say, you know, obviously based on engineering judgment, that's not going to be an issue. So those solutions will save people lots of time. There are acceptance criteria in there. Chapter 6, they're equivalent to what's in ASCE 41 as well as in the UFC. They specify the criteria in allowable rotations, ductility, strength. All right, so it's going to be, the standard will be released in the next 6 to 9 months. A lot of work by a lot of people. Level of interest, or level of usage will be interesting. You know, who knows if it turns out that Champlain Towers really was a progressive collapse event because one column or one wall section failed, then this could get a lot of traction. But if Champlain Towers occurred because of extensive corrosion in the structure, then that'll reduce the likelihood that it'll move ahead. So one question we'll probably talk about tomorrow is, can a successful segmentation approach be implemented? ASCE and SEI are open-minded, and they would obviously consider that, but it wouldn't fit within the structure of the current standard, so it end up having to be modified if there is a successful segmentation approach, or when there is a successful segmentation approach. All right, so last part of my call, last part of my talk. Do you know when I started, Dr. Adam? When I started my talk? Do you know when I started? Was it 4:30? Yeah, well, I don't want to belabor. Yeah, I'll keep this short. So, not surprisingly, after 9/11, there's lots of money to do research, and there's a bunch funded by Department of Defense because they wanted to protect their people. The NIST, the National Institute of Science, Standards and Technology, have a long and ongoing research program that started with the World Trade Center and has continued on. They've done lots of different areas. Department of Homeland Security was involved earlier. National Science Foundation was involved to a small extent. But because collapse hasn't occurred very often in the U.S. since then, the amount of funding and interest has waned. Again, Champlain Towers could change that depending on what they find. All right, so I'm not going to go over these. I've got a few slides just talking about projects that are relatively recent. The one that is semi-interesting, well, they're all interesting, but this one, threat-dependent response of reinforced concrete structures near collapse. A lot of times, and Jason and other people have looked at earthquakes, probably can attest to this, but you'll have a building that's made out of reinforced concrete, it's heavily damaged, and from an earthquake or from a blast, and you go away on Tuesday, you come back on Wednesday, and it's laying on the ground because during the day, the night, it continued to creep and continued to collapse, and then ultimately got to the point of collapsing. I was involved with a full-scale test program for a flat plate reinforced concrete structure that actually occurred. We went home from the test site on Tuesday afternoon, came back Wednesday morning, and the whole building's on the ground there. So she got a project to look at that and her results. She's just wrapping it up, but the results are interesting. And the University of Alberta, University of Texas, Austin, NIST has had, like I said, has a lot of ongoing projects. The last thing I'll talk about in terms of research is something that my company did. So the building, the testing and work that Dr. Adam has done on precast concrete was interesting because we had been involved with this also. We looked at a 3-story building. This is just a sub-model of it here. It's not as well detailed as the test item that we saw yesterday is detailed. Yeah, anyway, I can go into that, but it would take too much time. So we built a fairly detailed finite element model out of that, using the plans. And then we showed that the building wouldn't collapse with a column removal here. The displacements are magnified 10 times, that's why it looks so large. And then here's the crack and failure pattern in the slab right above the column removal. So anyway, there's an interesting analysis, and the results showed that in the test that Dr. Adam and his crew have run, shown that precast concrete can withstand progressive collapse events, initiating damage. And the reason why the DoD is interested in it is because there are there are only 2 buildings in all of DoD made out of precast concrete. I had somebody look at that. And the reason is that their reputation is that they are prone to collapse when you get extreme events. And so the DoD has stayed away from them, but they also recognize that they're missing out on a construction type that's economical and fast. And so they were interested in being able to use precast concrete frames. We had another project where we designed a load-bearing precast concrete wall system to resist progressive collapse also. And we're hoping to use that to get those into the UFC. So once it's in the UFC, then contractors will be willing to use those on a military basis. And then that is it, just as I'm cooling down. So anyway, thank you very much. That's right, I'll take questions at the end of this. Yeah, okay. Thanks.
Thank you very much, David. So we can move on to the next presentation. Professor Bing Li, are you ready or sleeping? So let me introduce Professor Bing Li. Bing Li received his PhD from the University of Canterbury, New Zealand. He has been teaching graduate and undergraduate courses in the areas of structural design, including courses on the behavior, design, and assessment of reinforced concrete structures at Nanyang Technological University, Singapore. He has research interests primarily in the areas of reinforced concrete, and he's also actively working in the areas of anti-terrorist design and evaluation for government and commercial facilities, and research and development blast testing for explosive effects on conventional reinforced concrete structures and buildings. So,
okay,
Bing, thank you very much.
Okay, thanks, Jose. I just wake up, and
yeah.
Thank you. First of all, very grateful for you to invite me to come here. I wouldn't expect to give a talk, and the topic choose proof by experimental actually is given by Jose. Jose say, hey, you do talk something about the proof experimental work, and so I have been working for experimental work for many years. Jason and I were the same thing, when I was young, sweating in the lab, do a lot of testing. But today, I try to do some casual talk. It's not really serious talk to share with our colleagues here, particularly, from Valencia University and the students here, and why we do the experimental work, and try to justify. Yesterday, we already visited the site and see the mega test set up in here. And the purpose here is really better to understand the mechanics. I think Tony, my friends Tony, we just met yesterday and already gave the very nice presentation about the European perspective way to look at the mechanics. We are also inspired by the European, particularly with the Deutsch, the trust modeling, and so what we try to use in this short presentation to give you a flavor about what kind of research we have been done for the last 20 years, why we need to do experimental work. Okay, can I control the slides or? Sure. Okay. So, Luca, this is Da Vinci's pictures about this. So you can see the topic side typical here is exploring the mechanics of the reinforced concrete structure. I think as Tony mentioned about this morning, why we do experimental work. It's basically, first of all, we have, Jason also mentioned this morning, we have some perspective on the structural load pass, how to flow, how the mechanism, how to be resistant, that eventually we try to using very selective experimental result to try to verify. But doing experimental is not so easy from my point of view. Okay, a lot of people say, oh, doing experimental very easy, I can do many. But yes, 100 people, everybody can do experimental work. But the problem is, do you know how to get data, instrumentation, how to interpretation the data, how going to transfer the design code. You open the reinforced concrete design code, in this field, I'm very ashamed to tell you that 95% of our design code is empirical. It's amazing, it's empirical. Only 5% are considered is theoretical, only torsion part, but still remain the elastic. We are training in New Zealand. Basically, we look at the structures, not only look at the linear elastic problem, also can look at the beyond the plastic behavior, how the force will be transferred, what the mechanisms be involved. Of course, that is why I'm using rough to the fine. A lot of people doing the massive testing. You know, you look at the Japanese do a lot of testing, hundreds beams, 300 beams, but eventually just simply using linear regression equation just presented. This is currently the code to say. I'm very sorry to say ACI is one of the example for do that. So I try to using the very short presentation to tell you what is our approach to do so. Is there any way we can using the very simple mechanics? Don't say simple, the physics phenomenon, and can explain the force transfer. Okay, I try to give you elaboration start from beam, column, shear wall, and eventually I touch a little bit progress collapse. Initially, when talking progress, yesterday after we have visited Jose's side, I decided not to talk because our scale is very small, very small. So let's move to the first topic. Maybe Tony like to hear that. This is a classical example. I think Uwe also interested. A classical example published by my supervisor, Professor Park and Paul's books, experimental work done in the Stuttgart University. Classical side. Now, so far we have many beams have tested. I just mentioned this morning about over 3,000 beams. Data are be published in the premium American Journal of the American Concrete Institute Journal. There were very few beams actually can be really be selected to do the very refined detailed analysis. But this picture would basically tell you that for exactly the same cross section, but if you vary the shear span ratio, you'll be found certainly different film mode. Very interesting. You can from the very bending fraction mode, you have an aspect ratio more than 6 or 4, and you go to the medium 1, 3, you can diagonal tension failure, and go to shear and shear compression failure. Finally, you go to deep beam. You can see the film mode will be changed. Film mode will change. As Tony already mentioned about, when you do strengthening the building, you start corrosion the longitudinal bar. The reason why she says so, initially designed for fracture, then can become a shear failure. And maybe initially designed for shear critical deep beam, after corrosion, longitudinal reinforced rebar, then become fracture failure. It's very interesting phenomenon. That is why we want to through the careful planning for experimental work and try to explain what is happening here. Now let me plotting the data you. I'm not scared for you. So this is I collect the data, massive now using that big data technology, machine learning to try to correlate or do the probabilistic assessments of the all people tested available data and also all available design method. You look in here. It's very random. This paper all published. You can get from me and from ASE, from the ACR. You look in here. It's very random. It's hardly can proposal for unifying the theory can predict the shear strength of the beam. Okay, can be vary with the different the shear span and the ratio. So what can we do because involves so many and very more. So this is recently I also look at re-evaluate the shear strength of RC beam. I look at the Spanish and you are also heavily involved. The EC2, you look at the EC2 here. It's not really well presented for shear strength of the beam. Even the shear strength, if the EC2 say, oh, you can using high strength concrete, you can using high yield strength steel, but there was no any proof data to support. Then you look at the ACI code, relatively better because the American design code has been changed every 5 years with the major amendments. Look at FIB and from EPF, from Lausanne, Montoni groups, they keeping promotion for FIP, MC, the concrete model code. Actually, it's far more better than EC2. I think Tony can share with your supervisor, Maury. He will be interesting to see, the EC2. He wrote a paper, I read. He start to critics on the EC2. I'm very support his idea. Should be re-examine the EC2 provision, even ECA. Lots of the equation is not really representative. You look at the data itself. You look in here. This is all data are plotting for that. So what can we do? Of course, we have to using the mechanics. We do a lot of testing Today we mentioned about UC Berkeley 1955, Richard Fennick 1969, Canterbury test. They provide for very refined data for us to look at the shear problem. And the first one, the angle, the shear angle, this is something I'm very interested in because you know the ACI code, even the model code, the shear inclination still using the constant angle model 45 degree. It's nonsense, you know, correct? But EC2 at least using variance model. Is there any way to calculate? Yes, we can calculate, but you look at the paper we published, it is very complicated. The mathematics model, you know, how to predict individual the inclination based on the cut section, you know, if compression, the neutral axis steps. So you can using the least energy virtual work, it can be predicted the inclination of the angle, of course. But nowadays, when you do the truss modeling, in our approach, Newtonian perspective, we are not only limited using the force equilibrium approach now. Because using force equilibrium post strength time model, you're not able to consider the contribution of the concrete. So you have to be coupled with the concrete contribution using the Mohr circle, which is using strength capability. So our model basically is not only satisfy the force equilibrium, also satisfy the strength capability. But it's a lot of interaction for inside. I think Michael Collins also did the modified compression theory, also in using exactly the same way. But we haven't moved to very detailed, like Wallen, look at the aggregates interlocking. Basically, we don't dare to touch because this is a very black box. I don't know what's happening. Even we don't know how to really talking about concrete contribution. Aggregates interlocking, compression zone, doorway action, who knows? I already reached this stage, say my door is closed. I don't want to be further because I don't think I can contribute a lot. The other one, we saw the experimental work, we found out the deflection. A lot of people say, hey, I test the beam, I found the deflection in this. Now, I want to ask you a question. What is the components of deflection here? Because some deflection is contributed by the fracture. Some is contributed by the shear. The shear deformation also is my recently hot topic. We published a lot of paper on the shear stiffness. And shear and fracture, how going to decouple? This is all through the different shear span ratio can be explained from the tension stiffening phenomenon and can be predicted. Particularly for long span bridge, you look at the deflection, it's not very much, but the shear deformation is the serious issue because the eventually trigger the collapse of the bridge. So the shear deformation is something we have driven. But if you want to consider for shear deformation, so you have to be using the so-called the truss model. We have developed the series types of the so-called plastic truss model, and based on thanks to the original the Deutsch opinion in coupled concrete contribution using Gaussian method, you cut a different angle model. We inspired by European profession, but we not be reached into the shear fraction, you know, but it's not a cross-section method. Why people say shear is difficult to research, fracture is easy. We are very proud to say we know 99% of our fracture, but we only know 5% of shear. The reason we don't understand shear very much because the shear is not the cross-sectional problem. It is the elements issue. Elements issue. This is why we have the B region, we have the D region. Eventually, in order to consider and the different part of contribution, we have to be cut in a certain part and using strain capability issue to link them together. So that's why it can be provide a rational way to explain to shear resistance for that. So this is the beam part. Basically, I'll just say the data is very scattered, basically. It's not really rational can propose one equation for that. Now here, then we move to another topic about column. Today nobody talk about column. The column is very, very important to the vertical supporting elements. Even in the Jose's testing, you have moved the column message. So when the column be damaged by the certain scenario, my opinion is may not be totally lost the totally vertical support strength. It's not really totally lost the lateral strength and also vertical supporting stiffness. So we have to do lots of the testing and I try to look at the different kind of filling mode. For now, I already gave up to using the strain ductility, this concept. I suggest you to more look at the probabilistic-based look at the failure mode. If I keep the structure still in a fracture failure mode, most likely the structure will survive. Will survive. You look at here, this is the failure mode I've collected. Everybody know that. I can see this is the basically fractal failure mode. Very, very fat and hysteria loops. And this is after you have this long, large drift, you come with a fracture in shear. So this is the purely plus hinge. This will be plus hinge coupled with a little bit the shear, half hinge. Now finally, you can see this is the shear failure. This is the shear failure during the earthquake. Very obviously, from the cracking pattern, you can tell that this is a not rich earthquake. In 1994, I will see this picture. I'll ask my students, do you think this is good performance or bad performance? A lot of people say it's collapse. No, I think it's very good. It can all follow the fractal crack. There's no shear crack. Can have such kind of large deformation will be there. And you look at the shear that we're testing in the laboratory in here, there's no any plus hinge. This is a non-seismic design column, and very obviously is a diagonal crack. And you can see once you reach the peak, engines immediately drop. So that was the 3 major failure mode in front of you. They can be just uniquely represented, and one may not be. If you have the large axle loading, you change the tension compression, varying the axle loading, your failure mode can be fracture failure mode, become a shear failure mode. So this is all mixed up. So is there any way you can be identified something we need to through the testing setup? This is testing setup. We're pushing a pull, and eventually we can using the actuator. We have, thanks to government support, we have 12 actuator, to basically can do all kind of versatile testing to try to prove something we thought this way cannot move. Okay, this is an example. Jason is supervising, he's a PhD supervisor. Professor Nigel Christie is very well known. I did not have privilege to study with him, but later on we become the friends. During the earthquake in Christchurch, Jason just tell me, Nigel sent me the picture about this. He said in Christchurch Cathedral Square, the post office, I found a crack vertically. I don't know what's happening. Can you explain to me? I said, I don't know. The later on, I sent the email to Jack Maley from UC Berkeley. He also said, don't know. So I try to, I also cannot explain why it will be like this. So I did the laboratory based on exactly the detailing. We tested the column again and found surprisingly, and the column with the certain X loading here, they will develop the bound slipping failure of the column. And initially try to start with a plus hinge and finally develop the vertical shape and separate the column in here. So this is why we found that the fourth failure mode is a splitting failure. So there's a lot of condition here is depending aspect ratio, column, loading history, can be to change the failure mode. So this is the column. If you do the calibration, the ACI design code and the EC2 design code, you also found that it's a large scatter. We have a published series, the paper, look at probabilistic calibration of the shear strength model. I collect all the data. We're not only simply just using linear equation to do the complete COV, SOV, but using Bayesian method, using Markov chain. This more advanced the data analysis coupled with the mechanics and try to analysis, can do apple-to-apple comparison here. Result mechanics, we're not able to judge other people's result to do this. So basically, you can see that a different design code, different researcher will come with all different conclusion for that. So how are we going to do with this? So this is a lot of the work in front of us. We have to, through this problem on the table, hopefully later on the people can be do more working on this and how to unify this design equation. So we gave the confidence level. Actually today, somebody, I think always talk about the probabilistic base. I very strong support probabilistic based design and the progressive collapse based on different scenario. Eventually based on you talk about the probabilistic density and gave you different the collapse scenario probability. And let owner to decide this. So we already have this technology basically can collect all the data, can give you 50% confidence level, 75% client level and 95% level. Let the client to do it. My work immediately assaulted by the insurance company. They liked my work, send to this. They say, this is very good. Can we have the progressive collapse insurance? I'll do that. Yeah. But for any scenario. So that's why you have to be deterministic, only have a certain scenario. But probabilistic basis, we can have everything is envelope to look at. How do you evaluate this kind of the scenario and the strengths? Now let's move to the another classic topic of beam column connection. Spanish don't have the earthquake problem. This is also very classical. The books 1975, by the Tampoli and Bob Park. I think this is the milestone for earthquake engineering research using capacity they design and tell the structure how to do. If you design with the British standard, if you design with the American standard, you don't know what structure will be fail. But if you according to capacity design, proposal in 1975 in New Zealand, and you can exactly purposely detailing the mixture structure will fail in this mode. I think Jose, your project also using so-called fuse subject also is this kind of philosophy, right? Tell the structure how to do. But Jason mentioned about it. Of a certain project when you sell it, say, hey, this one will become a potential risk area. Who am I going to buy, Jose? Maybe cheaper. Sell to me 50% price. I can strengthen that. So this is something the different mechanism will involved. But the Bob Park and Tom Polly did not tell you the probability for doing this. Okay, if you provide for detailing, are you sure structure will behave like this? Some people always ask me for this. So the modern trend have been pushed to the more probabilistic basis. You have to use in mathematics way to do that. And you can see most of the software when you do the structural analysis always think the beam column and joint is rigid. It's rigid panel, but actually it's not. Any building start to deform. Just yesterday I saw your friend start to remove. There were 3 components embedded inside: the column deformation, the beam deformation, and also the joint rotation components for that. I think Jason today is mentioned very nicely about the diaphragm action. Not many people realize that diaphragm is the very effective way to transfer the force one way to another. Without the diaphragm, the beam and column joint cannot work together. So the diaphragm rigidity is super important for that. The problem is later on is how to assess for residual strength and also the residual stiffness. This is something is very important. If you have any damage, did you totally demolishing them? Are you going to strengthening them? How many percentage of the probability can be fully recovered? This is a lot of the insurance company people want to know this. So basically, I already proposed we're using Shear from the traditional, you look at my PhD thesis 25 years ago, is a strength ductility. This is the keywords. Nowadays, you look at my paper later on, where everything is talking about a filament. It's a filament. If you want to have the strength ductility, definitely it's a fracture filament. It cannot be shear. This is why we need to get rid of the shear, even we don't know very much about shear, about this. Now, in the beam column joints, we have done a lot of work for the last 20 years. Also developed the plastic truss model, can be explained clearly about the low pass. This involves the bond-slip relationship, transverse reinforcement, mini strut, and this is also we're using various angle model. Thanks to the FEM program, thanks to the strain gauge rating, and we can able to correlate clearly with the reinforced test data, experimental work, and together with FEM coupled with experimental evidence. So that is why I gave the engineer a clear picture of the low pass, how the force will transfer from one side to another side. Through direct transfer from the strut or through the bond slip yield bar, basically penetration in the joints. So the mechanics is extremely important. The purpose here, if we do experimental work, is to try to confirm something we have to do. I think this is another professor from the SUNY block. I cannot pronounce your name, sorry about that. And you talk about the shear wall. As mentioned to you, shear wall is very vulnerable during the earthquake. Jason already mentioned about in Christchurch earthquake. And we also look at the shear earthquake in here. We have several different failure modes. We have the web crushing, we have the sliding shear, we have the shear tension failure, And some Filimo, like sliding shear, until now, I also don't know how to do that. I gave up. Before retirement, I want to do something, but I changed my mind. I don't do it anymore. I cannot do. Really, it's beyond my capacity. But for certain Filimo, we can also using the simple mechanics model can be explained very clearly and how the force will be flowing in the elements. So in the future, when we design the elements, design the components, I'm suggest maybe already retired, and me not using everything. We'll be using section method. We will be using for the section method strong time model. I can design more economically, can explain to how the force. Certain area around the low pass, you need a reinforcement, and the other pass may not be necessary. This is also applied to progressive collapse and things. You need to understand the low pass very well. And we also do a lot of work on the shear wall with opening and just try to prove that the low pass is very important. For example, if you have the shear wall with opening, you cannot use the section method to design. Okay, a lot of reinforcement don't know how to design it. But if you understand the low pass and with FEM and with your engineering judgments, eventually you can be detailedly, purposely put reinforcement around the low pass. This is a push and pull during the earthquake. And we can save 40% of the reinforcement. So my design, when we give quotation, my reinforcement always in the low side. Why? Because we understand the structure, how it works, rather than just blindly follow the design code. And if you look at the shear wall, we tested it in the NTU laboratory. We have a lot of people tested just the simple elements. We tested different shape of the reinforcement. And we push in different angle. You can see it be very, very funny and envelope and involved with a very, very different kind of the Filimo, because you don't know which direction the force will come from. Is the way we can be really to come with a rational way and can design the shear wall. After we doing this kind of study, and we can find lots of very interesting phenomena like buckling, out-plane bending, and the crushing, the certain things. This is all happening. Today I have lunch. I was talking to one of the ladies. I said, "Have you read Park and Polly's books?" He said he don't know who the Park Polly. I say I read Park Polly book like the Bible. Still reading. In 1975, these two gentlemen, our old generation, already point out, but not quantified yet. They observed the kind of phenomenon, but how going to avoid this one? How going to design them? They did not really mention at all. So a lot of the interesting things we be currently doing, particularly for the local buckling of the wall, observed a lot in Chile and also in Christchurch earthquake, and how going to do this one? Single layer reinforcements, debuckling the wall, and this is a very challenging project. Now, this is basically to tell you the experimental work is very, very important to help us the forming the design code. The last part, I have touched a little bit of things. Jose invited me for so-called progressive collapse, the project initiation, the workshop. I have given you a little bit, a few slides about we work. I think David mentioned about US 9 September 11. I started to research for protective technology since September 11. So we visited the United States. Government willing to give me the co-funding to a US Army, a US test station for over $1 million. We're doing the serious test from the column to the progressive collapse, to the impact, to the missile impact, to the contact charge. So this is the first testing together with Army. This is in my laboratory. This is why we invest $7 million with the Singapore Army, build my the lab. But currently, because I don't do testing anymore, a lot of the actuator is rusted. They want to send the Chicago to repair. I say better to dump there, just like a museum, let people know, our worst working there. You look at here, we have how many saturator here. Designed for this kind of setup, and you can see using Chino, after you do the contact charge, FEM analysis, and using helicopter, bring back to university, do the vertical setup. So we have to spend a lot of time to look at the correct, reasonable boundary condition to do experimental work. Field testing is necessary, but field testing not able to collect very reliable data. And after that, so my role become working with the US counterpart, basically test the skill model in a laboratory and try to correlate with their research. A lot of research not able to publish because this confidential, involved the TNT stuff. We still keep it, and so this is later on. And my student Chen Kai and I already have supervised one PhD student on the progressive collapse. He did quite well. We tested very seriously. This is 15 years ago. I'm using this kind of pin hinge now. This is the first paper we published engineering structures. 2012, I think 2015 or whatever. You look at the instrumentation, we are the first one tested corner collapse. I found the corner one may be very vulnerable. This is why we just sort of set up, basically using different hammer, using different machine, look at the dynamic amplifier factor. So this is the first things we do. After that, we try to this is the US project in the Albuquerque, New Mexico, and we spent $1 million, US part spent $1 million, we did a charge and then there. So this is exterior column, charge loss, interior column, and we built exactly the full scale structure based on the British standard. Singapore was a British colony, and we designed it. I using the scale model built in my laboratory and doing the similar setup and do the correlation things. We found it very successful in the laboratory. We spent very little money with realistic the boundary condition. We also can get similar results. Why we need to do this testing? But eventually, you look at the scale factor. It's not so sensitive. Can you help me to push? Next slide. Yeah. So basically, I look at we tested this the 2D plan, 3D frame, 3D frame with one beam, result slab, two span, multiple span. We test the series of this kind of the slab. Try to look at it fundamentally and how does the mechanism we developed, particularly for membrane action and continual reaction to that. So this is all related to the cast in situ structures. But actually, it's not relevant to Singapore. Singapore government banned cast in situ because our labor is very expensive. Everything precast. 95% is precast. So Jose, your research is very relevant to us to that. So this is in cast in situ because that time and we working with the US together and to looking for the slab effect. We have produced quite a bit publication and paper on that. You can look at the setup here. We have the column, we have the actuator, we have so many strain gauges, so many LDBT. With many students are not able to count in everyone here. So this is a lot of the works and the preparation, the works. So this is normally cast in situ, the slab. Can you help me to shift the slides? Previous one, next one. Yes. Then we move to flat slab. Flat slab is considered a very popular structure system for the condominium, and this is why it's very vulnerable to the punching shear. You can see we have developed a different loading. Yesterday, I have in the side, I have extensive discussion with Jose regarding how do you put the loading. Loading is very sensitive from this, and if you put a different loading in different part, and it will be yield with a different result. So this is very, very challenging, this one. So doing experimental is not so easy. We do a lot of the FEM analysis, basically finally select the so-called this octopus, is the way apply for one loading, uniform spread rate to the 8 legs. Finally, you can get this result. Next one. You will be bomb. So we not only look at for exterior column, we also look at the interior column. Yesterday I mentioned to Jose it all. We want to say if you interior column lost it, and how the force will be transferred to the adjacent column. This is something we have looked at, and how going to later on developed with membrane action. This is all possible scenario will be really happen. Next one. The precast we already published in one paper because it's a limitation of funding. We're not able to do so. So we found it very vulnerable. So this is the precast slab, the system we tested in our laboratory. Many complain, people are looking very messy on this. But from here, we're not able to using hollow core. We're using the precast plank with topping. Eventually, you can see the slab of the column lost it, and eventually it will drop, become much more very vulnerable compared to cast in situ slab. So the topping is very important. I think the Jason already gave a very nice presentation this morning talking about Canterbury diaphragm, the research. We always found the diaphragm is very, very important. But if you ask a Singaporean to give a 75%, 75 mm thicker, heavy mesh reinforcement topping, nobody wants it. Too heavy. So this is a challenge for us. But how are we going to cope with this one? We also did a lot of the loading arrangement. Jose, you can see this is using a very concrete block. And we test one slab model. Another one are using the lead, the metal lead, also water bag. We try several scenarios. We try to correlate them together. See, can find out the realistic test result for this. And setup also very difficulty at all. And we just use. I still prefer using something I've designed it, using the octopus way to apply for one loading. This is the cheapest way to do so. Eventually, I can be transferred to uniformly. Don't say uniformly, proportionally distribute to the other corner. We have a low cell. Eventually, we don't know how much force will be inserted for individual points for that. Next one. So this is my last slide. Basically, our research here is not only doing the research work in the experimental-based observation, we also do the mechanics-based and also the data-driven. Nowadays, many don't do experimental work anymore. I stopped doing now, but I look at other people's works too, and how we're going to evaluate them and how to improve the design code. This is one of the final objective. Okay, thank you, Jose, to give me opportunity to have a short presentation here. I wish my experience can be benefit for your project. Yeah, thank you very much.
Thank you very much, Bing. Well, during your presentation, you referred to some of the previous speakers, and I understand that you're willing to ask you something, but I would propose that we postpone this for a debate later.
Okay.
And Itsaso, are you ready for your presentation? Bing, thank you very much.
Yeah, thank you.
So let me introduce the next speaker. Itsaso Arrayago is a Marie Curie Fellow at the Universitat Politécnica de Catalunya, the UPC, currently working on the development of system-based direct design methods for steel structures based on system reliability, and her research interests span across the areas of structural reliability, advanced finite element analysis, material characterization of metallic materials, planning and execution of experimental programs, and development of design recommendations for structural codes. She's a member of the working groups of different panels of the Euro codes, mainly stainless steel and mainly finite element analysis and stainless steel structures. Itsaso, thank you very much for being in Valencia.
No, thank you for inviting me. Good afternoon. I promise I'll be quick, so we can all go and relax a bit, okay? So I'm the last, but I'm not the least. I'm also an imposter. I don't know if the reason is that we needed some material balance or some gender balance here, but what I will tell you today is about the potential of stainless steel structure against progressive collapse. Okay, so I will tell you a bit about some lessons that we have learned in the Fail No More project. I was not part of the project, okay, but my research group was. So when I got invited here, we thought that it would be a really good chance to explain a bit the project and the main findings that arose from here. Okay, so let's start. Good. Okay, so we've already seen that structural robustness is important, and it is nowadays addressed in most of the modern codes and structural guides, including the Euro codes. For example, in the Euro Code 0, we can find a couple of clauses referring to robustness. Basically, it says that the structure should be able to withstand accidental events without having a disproportionate collapse or damage, and that we should try to either avoid or limit this damage. Okay, so this information, it is not really useful for the designer. Okay, they don't know what to do with this. So there is a clear need for some design guidance, some recommendations, so they can really address these clauses here. So this was the aim of the Fail No More project. It was funded by the European Research Fund for Coal and Steel. The main objectives of the project were, one, and most important one, to produce these practical design guides and collect all of them in a practical design manual. Okay, and specifically it's devoted to steel and composite structures, so nothing related to reinforced concrete so far. Okay, and then in a second stage to translate all these recommendations to different European languages and to do some kind of dissemination action so everyone is aware about the existence of these design guidelines. So to propose all the recommendations, part of the consortium was expert on the topic, and they used everything available in the literature and some recent research projects that they have carried out. Okay, so here you can see a list of the partners or institutions that worked in the direct development of the design recommendations. You can see kind of big names here from the University of Liège, Imperial College, Universities of Coimbra, Stuttgart, Trento, Timisoara, etc., etc. Okay, so these people worked in the development of all the design recommendations, and this is the whole consortium in which we can find the original partners plus some additional countries such as the Czech Republic, Poland, the Netherlands, France, and also Spain, where my colleagues participated. Okay, and this team was responsible for translating all the work and disseminating it into the different countries. Okay, so the design manual is comprised by 4 different parts. Okay, the first part 1 is the main body of the document, which contains all the design recommendations, all the explanations on how the calculations should be done. Then we have part 2 with 24 worked examples, I think. We can find some steel and composite structures, both, and these are structures designed in seismic and non-seismic areas, so the casuistic is quite high. And then just a couple of pages with the annexes, with some coefficients and tables for the simplified methods, and a very extensive list of references, which I believe can be useful for the Endure project in the future. Okay, so this manual has been translated to 10 different languages, and if you are interested, you can download all the information from the ECCS website. I have added a QR code at the end of the presentation, so you can just catch it there. Okay, so the main body of the document, or about the design recommendations for robustness, is divided into 6 chapters. After a very quick normative context, we can find a flowchart that has been developed in this research project, which is aimed to assist practitioners in the design for robustness. Okay, and then there is explanation of the consequence classes, which are the basis for the design strategies that we should adopt in the design. Okay, and then chapters 4 and 5, they deal with the design methods that we should consider when dealing with identified accidental actions, such as impact, explosion, or exceptional fire and earthquake events, and also for unidentified actions to limit the propagation of local damage. Okay, and then there is a really quick chapter devoted to risk assessment, but nothing to do with what you're doing in Work Package 1. Okay, so here you can see the famous flowchart. Okay, so everything in the document refers to this figure. It is the backbone of the design manual, of course. So in this flowchart, they have tried to address all the robustness design process step by step. So the designers, they can just follow the steps and they can do all this process, like, you know, I don't know if it's user-friendly, but in an easier way. Okay, so obviously I will not go into detail into the different methods because I'm sure that you're more expert than I am in this, okay? But everything is really well explained in the design manual. It's about 300 pages, so it's a lot of information. Okay, so instead, I think that it's more interesting to have a quick look into a few worked examples and see what are the conclusions or the highlights that were brought up in the project. Okay, so the worked examples consider two different structures in non-seismic areas, one steel structure, one composite structure. It's a quite simple building structure similar to that we saw yesterday, okay, but it has 6 stories. And the structures for the seismic area are also very similar, but they have some modifications to comply with seismic design guidance with Eurocode 8. Okay, so they both are consequence class 2 structures, and they are subjected to the usual death, life, snow, wind, and seismic actions. Okay, nothing new here. So regarding the identified actions, the worked examples include calculations for the main extreme loading cases that we can think of. We have impact, external explosion, internal explosions, localized fire, and seismic events. Okay, and for each of them, they usually have used some kind of simplified or prescriptive method and some full dynamic analysis, so they were able to compare results and assess difficulty and accuracy in each of the process. Okay, and same for the unidentified actions. Here they have considered the alternate load method, the key element method, and the segmentation method very, very briefly. So I don't think that would be helpful for the project. And again, they have considered for the same situations and the same structures different approaches, so they were able to compare the results. Okay, so from all these comparisons, they have extracted some interesting, or what we thought were interesting conclusions or highlights. Okay, mostly regarding of the influence of the initial design in the final performance of the structure against progressive collapse, also on the comparison of advanced and simplified design methods, some limitations on the prescriptive method, the influence of the joints, of course, and some benefits of the composite action in composite structure. So we will see each of them with a little bit of more detail. Okay, so regarding the influence of the initial design, it was evident, of course, that the choices made in the initial design had a large impact on the response of the structure. More in detail was the construction details, such as the orientation of the columns or the configuration of the joints, which had the highest influence. And for the seismically designed structure, it was also shown that basic seismic design principles, including regularity, continuity, lateral strength, ductility, and failure hierarchy, provided a very good properties in terms of robustness to the structure. Okay, so as we had stronger columns, we could have better protection against impact and explosion, and the flexural and ductility requirements for beam column joints provided also with higher capacity in the column loss scenario. Okay. So regarding the advanced against simplified methods, the examples showed, because they were validated against experimental results, okay, that the advanced methods were able to capture very accurately the response, or the real response of the structure, and because of that, in some cases, they were able to limit or avoid the requirements for retrofitting the structure. Okay, for example, here you can see very briefly the results for an external explosion. Okay, it's affecting the column here. And so the advanced analysis are predicted total displacement on the column of 24 millimeters, which was admissible according to the failure criteria that was adopted in the project or in the problem. Okay, but if we used the equivalent single degree of freedom approach, like simplified approach, we would obtain displacement of 87 millimeters, which would obviously require some retrofitting. Okay, so in this case, even if the advanced methods are more complex and it's more sophisticated and more difficult to do them, we will have some gain here. Okay, so again, regarding the limitations of the prescriptive method, okay, the project showed that the tie-in forces that are calculated using the method in the Eurocode were much smaller than the ones that can be obtained using the analytical approach or the full numerical approach, which consider the explicit loss of the column. In this table, you can see the comparison where the loads predicted by the prescriptive method are roughly 10 times lower than the other ones. Of course, this is not probably surprising to you, but it was for us at the beginning. But this was just because this method is not aimed at predicting the loads due to the column loss, but to provide some minimum continuity to the structure. Okay, so if the goal of the problem is to predict these loads, to design the structure accordingly, we should use not the prescriptive method, but some alternatives, which can be the full numerical approach or the analytical approach, which also provides very good results and can be very useful or handy for practitioners. Okay. So joints obviously also show to have a very strong influence on the global response of the structure, and for that the design manual recommends to follow all the recommendations that are listed there in order to guarantee a minimum of ductility and rotation capacity or deformation capacity. Okay, this is an example of the same column loss scenario. Column is somewhere here in the middle, and the graph shows the comparison of the capacity of the structure if we use simple pin joints with orange, and then if we use partial strength joints in black. So the increase in capacity is considerably higher. Okay, but the advantage of using partial strength joints, if we are able to guarantee that they have the sufficient rotation capacity and ductility, is that we can still model the joints using pin connections, which doesn't affect the calculation much, but we can profit from this extra resistance if we need it. And finally, regarding the composite steel concrete composite action, the comparison of the equivalent steel and composite structures, it showed that when this composite action entered or worked, okay, there was some kind of additional redistribution capacity to the structure, and this reduced the local damage and the risk of progressive collapse, especially in the case of column loss scenario. Okay, and here again, you can see the comparison of a steel structure, which definitely collapses, and the same structure in a composite configuration shows a quite stable and relatively nice behavior. Okay, so that's, I promised I would be very quick. With this link and the QR code, you can download the manual, you can download lots of presentations, document with all the worked examples, like very detailed, and I think it's a good chance to download them now before you forget about their existence. So thank you very much.
So thank you very much, Dr. Arrayago. So you can download the manual if you want, okay? So, well, I like to close this workshop, and, well, if you want to debate, I would say that we close the session, YouTube session 2, and then we have to debate in an informal way if you want, okay? So I have no words to express my gratitude for your presentation, for being in Valencia, and thank you very much, and I hope that we can meet again in a couple of years here, okay? Thank you very much.